Hey, hi everyone.
Good evening, sir.
Good evening. Okay, I think for MLT also I can see some faces, maybe or voices from the MLF, right? Some of you are actually joining in MLF sessions also. Similarly, for MLF sessions, I think I took two sessions previously. Oh, sorry, I think one session, right? Yeah, one session for MLF. I think I seen. Okay, for MLT again, I'll be doing. I think this is the second session for this term. Yes, Iraf, yeah, you wanted to say something?
Hi, sir. Good evening. Sir, I want to know what is the syllabus of quiz one? Is it from week 1 to 4 or 1 to 5?
1 to 5. Uh,
So this from this term onwards, is it changed?
yeah, so it will be like changing. So currently, why it is week 1 to 5 is the reason behind it is I think uh, the gap for the first quiz, right? I think it is a little bit like too much, right, to study. If you
Very less gap, yeah, sir. Just
not
from
less
13
gap, I think.
July. Yeah, very less, sir. With 13 July, we
But
have quiz one, and then quiz two is
yeah,
on
between
September.
quiz one and quiz two, it is lesser. But for
Yeah.
quiz one, I think it is pretty high, right? Like, okay, I think it was
Oh,
started
we got a lot of
in
time.
the
Yeah.
right. So I think, and that's why, like, assuming that you have gained some, confidence in week 1 to 3 at least, and that's why uh, you may get like good amount of time to work for week 5 and 5 also, right?
Okay,
And again, that week 5 will also come in for quiz 2. So the syllabus for quiz 1 is week 1 to 5. Quiz 2 is 5 to 8 as usual.
so, sir, is it for this term only?
No, no, it will be changing like as we get like time, right? Like, so it will be changing. So now it is not going to be fixed from here onwards. So until now, I think it was kind of a template, right? So every time quiz one is week 1 to 4, quiz two is 5 to 8, and term is like all the weeks, right? And accordingly the weights were there, right? Weightages were there for in term. But now it might not be the same. Uh, the reason behind it is like there are quite a few reasons. One of the reasons is this I told you, right? So this time we had like enough time. Another reason is most of the time what happens is students they study from the previous terms, right? Previous term quizzes, and they wanted so if you do it like 4 or 5 terms question papers, and the similar kind of questions will be coming into the quiz, and you will go for it. So without understanding the subjects, or possibly you will try to solve the questions based on the uh, like if you do solve questions for let's say 3 or 4 terms, and then you score good, right? But does that uh, improve your understanding of the subject, right? So that is also one of the key understanding for us. Like, okay, we wanted it to change so that if the syllabus will be changing, so accordingly you'll have to put in some efforts in there, right?
Sir, it is for all courses or only
Yeah,
for
yeah, yeah. No, so it will be like varying for courses to courses. It's not like the similar pattern. I think for MLF MLT it is week 1 to 5. For some of the courses, I think since week 1 to 4 is the
Yes, sir.
dependency, and 5 to 8.
Ja-
Yeah, so you cannot ask week 5 for that, right? For few of the courses.
yes, sir.
So
So, one
there.
last question. What is
Hmm.
the weightage of week five? Like, obviously, we have to do the
Hmm.
PYQ also.
Hmm.
So, how many questions? Let's say 20 questions are coming. So, how many questions are there from week five?
I don't know, but I need to check. But
Maybe they
you,
have
you
equal
can you
weightage.
can you can
All week.
think of, yeah, you can think of like that. Yeah, equal weightages is fine. Yeah, maybe see we'll discuss about the weightages and all like maybe next week or something whenever we, dive into week 5, or maybe during the revision sessions, right? Fine.
Okay, sir. Thank you so
Yeah.
much. Yeah.
Okay, so I think we'll start for this summary session. I think okay, I got like some queries from the students that in our summary sessions mostly the similar type of things will be taken for MLT, like whatever sir has explained. but reason behind it is like sometimes students don't understand it from there, like fully not understanding from there. So I'll also try to get it for that. Like, but see, this is the first time I'm taking for for MLT, right? This term. So you tell me what changes. Maybe you wanted it for the next sessions. We can do accordingly. Right. So today what we are going to do is whatever sir has done, I'll try to get it done. That, but assuming that you guys have watched the lectures. Have you gone through the lectures? Right. Okay.
Yeah, yeah.
And I think all of you have completed your stats too. So can I safely say that you are fine with? Huh?
We have completed, but very
Yes,
we
sir.
have completed.
Yeah, but only one thing I wanted it from you is that Bayesian estimator. Are you familiar with the Bayesian estimator? Like what is
Yes.
We
prior, what
have
is
done it, but it would
posterior?
be better if you flash back once again, then we proceed by
Okay.
the likelihood functions only.
Fine. Okay. Okay.
And
So
second thing, in the I think the exemplification and the course content, there is no exemplification of the numerical data. If it is possible to
sorry. What is it?
examples of the numerical data is not there in the lecture also.
Yeah,
So
but
if
I think we will be covering that into our these sessions, right? Some of the questions
yeah,
will
in the live sessions, if it is
solve
possible,
with us, but solve with us we
so
do it, right? Some of the questions.
yeah, yeah, some questions it is there
Yeah.
because
Uh,
understanding becomes clear with the example of the numerical data.
yeah, that's true. Okay.
If it is possible somewhere it is required, then we can do.
I think we
But,
do in solve with us. That's what I understand.
okay.
Because the solve with us sessions mostly the
Yeah, in the
numerical
solve
should be there.
in the solve with instruction it is there,
Huh.
but at the time of understanding the concept,
Okay.
it takes time. And in the meantime, the time passes. So if in the
Okay.
beginning we take one example at least for the one concept, then it will be fine.
Okay. Fine. Okay. Have you gone through the lectures? All the
Yeah,
lectures
gone
week
through the
four.
lectures. Only
Okay.
one or two lectures are left. Only.
Okay. 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 This is slightly complicated from I think week 1 to 3, whatever we have seen. Slightly complicated. Why I'm saying is, if you are not very familiar with the statistical concepts, it may feel that okay, it is a little bit complex. But all these things, right? We have somewhere, I think in stats or maybe stats 2 or in MLF we have covered it. But I assume like some of you are not completed the MLF course also, but fine, nothing to worry about there. uh, let us start with the estimator techniques, right? Is that fine? So in general, what is the setup for estimator? And okay, first of all, what is parameter estimation? I'll just for 15-20 minutes I will discuss about this, and then we see the EM algorithm. Okay, so what is parameter estimation? uh, can anybody tell me, like, okay, first of all, what is parameter and why we need this estimation? Can you tell me that for what okay, is it related to any kind of distribution, probability distributions we think of,
Yeah,
right? Okay, so parameter estimation is related to the probability distributions, right? What kind of probability distributions we have seen earlier? Maybe we have continuous distribution and we have discrete probability distributions, right? And which all the famous distributions we have seen in discrete?
that is it.
Bernoulli,
In the
Bernoulli,
Bernoulli's,
right?
Bernoulli's,
But
normal
Uh,
distribution.
no, discrete. I'm talking about discrete.
Bernoulli's
but
Binomial,
Yes, fine.
binomial
okay. Geometric distribution
geometric binomial Bernoulli's
and
Gaussian.
Gaussian is not a discrete
Yeah,
distribution, right?
Poisson,
that is
Poisson.
continuous.
Poisson distribution, right? So
That's all.
these and maybe you have seen negative Bernoulli, I don't know, or maybe hypergeometric distributions, right? These kind of distributions we have seen for discrete distributions, and these are the famous ones. Most of the distributions, like let's say Bernoulli, binomial, and geometric, they are related to each other, right? It depends on, let's say, or they are kind of a family of a Bernoulli distribution, I will say. Is that correct? Because you will take each of the trial will have, let's say, coin toss, right? So you have head and tail, and then you perform that multiple times, right? And that's why that from there we have different distributions, where one is Bernoulli, another is binomial, another is geometric, let's say. So in binomial distribution, what happens here, the probability of success will be same throughout, for each of the toss, and the number of trials are fixed. I hope you all of you know that part, right?
Yeah,
So
yeah.
let's say you have a coin, a coin, and you toss it for 10 times. So each of the toss, right, the probability of success will not change, right? It will be the same, right? Another thing is the number of tosses will be fixed here. The 10 tosses, when I say, will have to toss a coin for 10 times. And what you measure later on, how many number of successes are there. Assuming, let's say, getting a head is a success, then how many heads we get out of the 10 tosses, that will be your that will be your probability for, let's say, if I wanted to find out probability that x equals to 4, and where x is a binomial distribution, binomial uh, random variable, right?
Yeah.
That is your. And what about geometric? You toss a coin until you get a first success,
Until get a success, first success.
right? That is your Bernoulli distribution, and generally it's what is it like? Okay, I haven't talked about probability distribution. So for Bernoulli, what is the probability distribution, or PMF, probability mass function? That is, okay, I think all of you have seen this. So Bernoulli, what is the probability mass function for Bernoulli? That probability that, let's say,
P
x
into
equals
1
to,
minus P.
it will be P when x equals
If
to
x is
X
equal
equal to
to
1
1,
and
1 minus
1
1
P,
minus
minus
P
P
when
x
x is equal
equal
to
to
0.
right? This is my probability mass function for Bernoulli distribution. Okay, what about the binomial distribution?
N choose K,
Right. So it
P to
will
the
be
power K1 minus P
choose k, let's say, and p to the power k, and 1 minus p to the
minus
power
P to the power
n
N
minus
minus K.
k, right?
N minus
And
K.
where n is the number of trials,
Number of trials for the first
uh,
success. Till first
not
success.
not first success, that is geometric distribution, right? In
Okay.
Bernoulli, in binomial distribution, this number of trials are fixed,
Yeah,
correct?
fixed. Yeah.
Okay, and then what is k here? How many successes you want, right? That is your, it will be varying from 1 to n, right? uh, uh, I hope this is fine for you.
Goal.
And
Goal.
yeah,
Yeah.
and this p is
Probability.
probability of
Probability
success.
of success.
success, right? Probability of success. Okay, one major thing about this distribution is, we assume each of the toss as what? Can we say that it is IID Bernoulli distribution?
Yeah.
Independent.
Yes, sir.
So
Identical,
what is IID means? It is
identical and
Independent and
independent.
identically distributed.
so. What does that both? What is the meaning of for both these statements? What do you mean by identical?
I
It
think
will be same.
for
Huh?
each of the
Everything is the same.
So identical means whenever the toss happens, right? The probabilities of success will not change, right?
yeah.
For each of the toss, the probability of success is remaining same. It does not,
Always same, it is half.
right? So let's say half or whatever, like it doesn't matter. Like let's say what is, if it's 0.2, 0.3, 0.4, 0.6, we don't know, but whatever is there, it is same for each of the trial, right? Independent is what, and independence is that condition is that will keep it
One trial
like
is
the same, right?
independent of the others. It will
Yeah.
not
So
affect the next one.
right. So let's say if I get the probability of success in the first toss as zero point 0.6, it does not affect the second trial, right? That is what it means. Okay, this is IID. So this is IID is the very important thing when we think about maximum likelihood techniques and all, right? Right. Okay. There is another distribution we will talk about is geometric. Fine. So geometric, what is the probability mass function for geometric distribution?
1 minus p
Uh,
raised to k minus 1
uh, and p.
into
P to the power k.
Not p to the power k, only p, right? Because we
Yeah, only
toss
p.
it,
Yeah, yeah.
toss it until we get the first success. Let's say you
Yeah,
have
p. P to the power 1. Yes.
so if I get the first success here, then each of the previous tosses I didn't get the success, right? And
Yeah, yeah.
what
P
is the
to the 1
probability?
and 1 minus p to the k minus 1. Correct.
Right. Okay. Fine. So that's it here also, and here also I think we assume the same ID principle. Okay. There is another one which is I think let's say Poisson.
Twice.
And what is the probability mass function for this?
E power
e raised to
minus
minus
lambda
Hmm.
lambda raised to k
Lambda to the power
P to
k.
the power lambda and lambda raised to the
k
power
factor.
k.
So
K
each
factor.
of this what is lambda here? It is average. Let's say if it is we think about the average, or you can say the rate. It is a rate parameter, right? uh, let's say average amount of time required to pass the
Yeah, yeah.
vehicles or something like that, right? So this is a
Average
rate parameter, right?
rate of change.
Not rate of change. It is a, let's say if I'm just looking for how many vehicles are passing at a signal, for example, right?
Mm-hmm.
So or let's just say if you are in a queue, so and if there is one service station and number of peoples are getting served there, for example, you are in a pizza shop or something and somebody is serving you pizza, so average amount of time required for a person to get a pizza, right? And that average amount of time, or in case of the vehicles, average amount of time to pass the vehicles, right? Or like certain number of vehicles, let's say. All of this are the are can be said as it is a lambda parameter. So it
So
is
whether it is average amount of time or within a fixed time, how many people are
that also you can say, yeah, it can be said like both
which
ways.
variable? Yeah, which
No, no,
variable is
both are
constant?
fine. Both
Time,
are fine.
time, no. Per
No, no,
unit time, no.
no.
Normally we
Space,
use
it
per
can work
unit
for
time.
space also. It is not like
Okay,
you cannot say that only for time, fix a time and check
okay.
for this,
Anything
right?
you can
And
use.
yes, fine. Okay, that is fine. So all of these are your uh, common distributions in a discrete manner, right? What are the continuous variables?
Lambda is the rate parameter. K is the
K is like how many it's kind of
trials,
trials, right? Like number of trials. How
number of
many?
trials.
Yeah. So let us say what is the? I think I have written it wrongly here. Maybe I can write it as K.
Yeah, S
The
is equal
probability
to
that x
K.
equals to K. So how much time it will take for serving for, let's say, 3 customers or something like that, right?
Correct, correct.
That kind of variable it is fine. So this is your discrete random variables. Uh, One of the important okay, another thing, okay, these are discrete. There are few more discrete, but okay, doesn't matter. Just talk about continuous parameters, continuous distributions. What are the known continuous distribution? Very famous.
Normal,
Okay, normal distribution, right? Normal Gaussian, you can say. Okay,
Gaussian, normal.
Sir,
it is same.
exponential.
Right, exponential. So what is the PDF for normal distribution? 1 upon
1 by under square root 2 lambda sigma
Sigma under root 2
E
e to the power
power
minus 1 by
minus
2 x minus
square by
mu
2 sigma
upon
square.
2,
right?
2 sigma x. Yeah.
So this is a PDF, right? And what are the parameters here? So mu is the mean,
mean.
Mean.
and sigma is, sorry, not lambda. Sigma is
Sigma is the variance.
variance or standard deviation. Sigma square is
A
variance.
standard deviation.
Sigma square
Standard
is the
deviation.
variance. Sigma square is the variance.
Then there is another known, which all we know is exponential distribution, right? Okay. What is the probability of probability mass distribution, probability density function for this PDF, it is lambda e to the power lambda x. Again, this lambda is a rate parameter, I can say. Fine.
Lambda is
You can say it's a rate parameter. Generally,
This
it
is
is
the rate
similar for Poisson and exponential. I think
Poisson.
they sometimes they are like we can use them. So one of the what is it? One of the so it is kind of a inverse we can think about, like when we think about the lambda in Poisson, right? So the average rate in exponential will be inverse of it, right? Okay, that is there, that one of the characteristics of these two distributions. But the important thing I wanted to tell all of you is why I have written all of here is, so in Bernoulli distribution, what is the parameter? P is the parameter, right? Probability of success is the parameter. In
Yes.
binomial distribution, what are the parameters?
NP.
P.
N
P.
and P, right?
P.
N and P. The here it will be having two parameters, right? N and P. Geometric distribution, how many parameters are there?
P1.
One parameter, which is P.
P
And Poisson distribution, how many parameters are there?
Lambda.
One, that is
Lambda.
lambda. In normal distribution, how many parameters are there?
2.
Two.
Mu and
That's
U
mu
and
and
sigma.
sigma square.
mu and sigma.
And exponential distribution, we have one parameter, which is lambda.
lambda.
Right? So now we know that if I get to know these parameters, I can understand about the shape of the distribution, right? Is that correct? Whatever the statement I'm having, can I say that
Shape of the distribution.
Yes.
shape of the PDF, or let's say shape of the PMF, like that, or maybe you can know about their expectation variance, everything, right? So if you know the parameter, you know about the distribution, right? Understand?
Yeah.
Right. So you know all the characteristics of the distribution based on those parameters. So parameters are the essential characteristics for the to define any distribution, right?
Distribution, yes.
Right. So if I wanted to so other way around, what can we say is that, let us say you draw some samples from that parameters. I hope you understand the sample and population thing. So it's like population is what? all
Total.
the all the all the all the all the
All the
samples,
data
I can
points,
say,
all the
all the
data
data
points.
points in the, let's say, uh, belongs to that
Sample
distribution.
is the training type of data.
Okay, so so sample, you can say that it is a subset of the population, right?
Population, correct.
So if you know that there are few samples, okay, if you don't have any understanding of the population, let's say you have a huge data about the population, and you don't know what the distribution is, but you know there are few samples from the distribution, right? So if only on the basis of those samples can we able to say something about the distribution, right? That is the question. So suppose there are x1, x2 up to, let's say, xn samples which are drawn from the some distribution x with some parameters theta, right? So theta can be like, theta can have more than one parameters, right? It can be theta 2 1, theta 2, or more, right? Because we have seen, right? So different distributions will have different parameters and different number of parameters. Is that correct? So Bernoulli, we
Yes.
have only one parameter. Binomial, we had two. Similarly, normal, we had two, and exponential, we had one parameter. So let us say you have the information about the sample drawn from the distribution. Can we say something about the population distribution, right? And
Parameter.
how can we say about the population distribution? By saying something about its parameter. And that is what the techniques come in. Is like there are techniques which are what those techniques are called as the parameter distribution techniques, right? Somebody has raised the hand. Yes, Kavya.
Hello, sir. Am I audible?
Yes.
Okay, sir, the x1, x2, xn, these are identical and independent distributions.
Right.
So, sir, you said that
Not distribution. These are the samples coming from an identical and independent distribution. So X is the population, right? So let's say this is the population density, okay, and these are the samples I'm drawing from the population. Yeah, now you can. Yeah.
So, as you said, it's identical. So, the parameters, I mean, you said that they will have different type of parameters or different number of parameters. So, sir, the parameters shouldn't be same as they are identical.
They should be same, right? No, what I'm talking about is, suppose let us say these samples are drawn from, let's say, normal distribution, okay, and normal distribution is characterized by these two, right? These two parameters, correct? So that means the number of parameters in this case will be how many?
Two.
Two parameters. So these two parameters are same for each of them, x1, x2 to xn. Fine.
Okay,
if
okay.
if I'm changing the distribution, let's say you have this distribution as exponential, then you have only one parameter, right? So the number of parameters are only one, but that parameter is same for all. That is the assumption we are making. Is that fine?
Okay, so x1, x2 till xn, everything will have same.
Same parameters. Sorry, same parameter, you can say, right? Because what we are saying is all of these samples we are actually drawing from the same distribution. Let us say you have 5 values, okay, 5 some random values, and what I'm saying is, I assume that these 5 values are coming from a normal distribution, okay, fine. So if somebody has given me randomly these values 5, 6, 3, 9 and 8, okay, what I'm saying is these 5 samples, they are coming from, let's say, IID normal distribution with mean mu and variance sigma square. Fine. Okay.
Yes, sir.
Now, what does that mean? Each of the sample drawn is from a same population. Fine. When I say that same population, that means the parameters associated with that distribution or that population will not change, right? If they change, then what does that mean? Then I am drawing the samples from different populations, right?
Yes,
Because if any population is there and if it is having some distribution, probability distribution, it should be same, right? The parameters for each of the values, it has to be same, right? Then only it is possible, correct?
yes, sir.
So if I have this normal distribution and now I have drawn, so let's say these values, right, these samples. So if I say that it is only coming from single distribution, then it will have only one these two parameters, right? If I don't assume that they are coming from there, what will happen? Then each of this will have different distributions, right? As mu and sigma square will change, the shape of the parameter will change, right?
Yes.
So that's why we wanted to assume that, okay, no, whatever the samples I'm getting, they should belong to a
Same
same
population.
same population. And when I say that, then these two conditions has to satisfy that they should be identical and they should be independent from each other, right?
Okay.
Okay. So now I have only these 5 values, right? But my population could be like a huge number of values. But whatever the population is there, if I know its mean and if I know the sigma square, if it is a normal distribution, then can I talk about all the values inside that population? Right? We can, right?
Yes.
Because
Yes, we
I
can.
have a PDF and let's say
But
I have a normal.
how will get this mu and sigma square from this only 5 data?
Right. So that is what the question is, right? Only from these 5 samples, how can I estimate the parameters, right?
And
Now,
how we will know from this, because it is unsupervised data. So how will you able to know that this is a normal distribution, this is a Poisson distribution, this is uh, descriptive or this descriptive? How we will analyze this?
yeah, that's what we are going to see those techniques, right?
Okay, okay.
What
We
are
are
the
going to
techniques?
learn
Yeah,
this one. Okay.
fine. So this is the question to you, right? Now that means you observed this. So what are these values? This is called as observed data, right?
Yeah.
We have observed these values, right? And what we are assuming is that this data is generated from
The
some
population.
population, or can I say that about some probabilistic model. Now what things are unknown to me now?
Which model?
Any probabilistic model, because
Yeah, probabilistic. Yeah.
right, because this is normal distribution, right? Anyway, normal distribution or whatever distribution we talk about, they are probabilistic, right? They
Yeah.
are not deterministic. We are saying that okay, whatever there is for each of the value coming in, it will have some probability associated with it. Is that fine?
Yeah.
Okay.
We are not knowing that. We are just assuming that it may happen like this, right?
Correct. Right. So now these are the two parameters which we wanted to find out, right? So different techniques are there to estimate about them. So whatever guess we are doing it, like see, anyway this is going to be a guesswork, right? So without the entire data, I will not be able to get the exact value of these parameters, correct?
Yeah.
Whatever we are getting is, maybe it can be a guess. Let's say you can say that okay, I can say this mu might be 3 and sigma square might be 2, fine, or sigma square might be 3, or I can say not 2 or 3, maybe 4 or 9. So if I say 4, sigma square is 4, that means the standard deviation will be 2 and the mean is around 3. So from that distribution I got this. That is my guess. But is there any sophisticated ways to solve this? So there are, and I think we have learned about those in stats 2. One is what? I think this was method of moments. So you remember this? Uh, this is called method of moments estimator, right? MME. There is one
Yes.
which is MLE, which is maximum,
Likelihood
Maximum
estimation.
likelihood estimation.
right? Maximum likelihood estimator. Okay, and another thing we have learned was that Bayesian estimator, right? Fine. So in this course, we don't need this method of moments. If you wanted to learn, you
Which
can.
one will be required most in our this course? Because we
These
have done
two,
it, but we do not remember
yeah,
everything.
yeah. These two will be required for us, right?
So
So maximum
ML.
likelihood and the Bayesian estimator.
Yeah. Okay.
So we'll learn about Bayesian estimator little later. So first of all, we'll try to learn about MLE.
ML.
What is it? MLE. So what the name suggests to me? Maximum likelihood estimator. What does that mean? I wanted to find a likelihood, right? And whatever the likelihood I'm getting, I wanted to maximize that likelihood. Is that fine?
Yes.
So what is the physical meaning of this maximum likelihood estimate? Physical meaning.
Physical meaning in the sense, what do you want to
Physical in the
understand?
sense of what we get from this estimation. Suppose we just apply the functions like the product of these all these probabilities, okay, and just calculate it. But physically, what we get from
So
this?
okay, so let us say whatever these values are there, right? Suppose
Yeah.
this 5, right?
Yeah. Yeah.
uh, or this 6 or this 3 or this 9 or this 8, right?
Yeah.
What we
Yeah.
are saying is whatever I'm getting here, right, it is characterized by these two parameters. Is that fine?
Yeah.
Right? So that means this value is dependent on some probability, right? So what is the probability associated with this value of 5, right? There is some probability. Let us say uh, if I know entire distribution, suppose think about this, like let us say this is your normal distribution, right? With let's say mean as 3 and
Yeah.
sigma as 2, fine.
2. Yes. Yes.
So can you tell me about what is the probability that uh, x equals to 5 or x1 equals to 5? If I know this 3 and if I know this 2, can you able to tell me the probability of this?
Yeah, because this is the parameter of this normal. If it is a normal distribution,
Right.
then we will be able to find it,
Fine.
right?
Okay, that's right.
Yeah.
What about the? Oh, sorry. Okay, I just did it wrong. So let's say 3 is here. So that means 5 should be here, right?
5 should be right side,
And 6 might be somewhere here.
Yeah.
3 is again this point. 7 or 8 and 9 will be here, right?
Yeah.
So, but if you uh, think about it clearly, or like, so what is the probability that x equals to 3 will occur? It's 0.5.
Yeah.
5 will be little over 0.5. I don't
Yeah.
know whatever but it might
Yeah,
be
whatever it
more
is,
than
yeah.
that. 0.5 or 6 will be having higher probability, 8 will be higher, or 9 will be higher, right? Kind of like that. Right. So if I think about it, it's or sorry, I think we are getting the highest probability for 3, and maybe
Probability will
like,
be lower, no? 5, 6, 8 will be lower, no?
yeah. So 9 will be like much lesser
Lowest.
probability. 8 will be like little lesser than that, and like that.
Mhm.
But see, if how can I say about this is because I know the mean mu and sigma equals to 2. But in this case, do I know anything about it? About the mean and the sigma? No, I do not know. So what we are saying is try to find out or try to get. So since I know that it's a normal distribution, I wanted it to have the maximum chance to occur these values, right? So find out the occurrence of all of this thing, all of this sample, right? And try to maximize the chance. Is that fine?
Maximize the chance of what?
Chance of getting these values, getting the value 5,
This
getting the
value,
value of
okay.
6,
Chance of getting these values
right.
with the application of these parameters.
Right. So how we do that? Like, let us say I will try to. So suppose I wanted to find likelihood of in this case mu and sigma square, right?
Mm-hmm.
And
Can I explain to Srikanth? I
yeah,
know him well, so I can probably communicate a little.
Yeah.
Srikanth,
Yeah.
this likelihood is nothing but a probability. Okay? Let
Yeah.
us assume that you have 2 coins,
Yeah.
or you have 2 bits of information you are going to try to send it to me.
Mm-hmm.
The probability of they getting lost is P. Okay? They are independent.
Mm-hmm. Mm-hmm.
I may-
Yes.
What is the probability that I will get both of them as wrong? It will be P square, right?
Yeah. Aspire. Yeah.
1 minus P
Multi- multiplication. Multiplication.
square. Now, if I want to maximize the probability of I getting both right,
That is
that
P
is
aspire.
called a maximum likelihood of this happening. Okay, we assume some parameters which we call that as a parameter going to be anything which we are yet to discover, but assuming that parameter is whatever it is, we are observing the data to be what we have seeing it. What is the probability that this can happen? And this probability we are maximizing for the parameter. So the likelihood is nothing but probability. We are maximizing the probability of the data being observed.
Okay.
Okay?
Got it. Got it. Maximizing the probability of that.
Correct. But because we already have the word probability associated with the parameter, we are using a little different word called likelihood. That's all. Conceptually, that is the meaning.
Okay.
Okay?
Okay. Maximization of the probability of that
So,
existing
Set.
data.
The resulting set. The resulting set.
okay. So
Probability is assigned, probability is connected to the individual event.
Yeah.
Here we are looking at the data.
And the parameter is still to be defined.
Correct.
Based on that data.
So that's where we are using a slightly different terminology called a likelihood.
Mm-hmm. Yeah.
It means the same, underlying concept wise.
so what we are finding out here is
Okay.
what is the probability
Let
of
us proceed.
yeah probability of
Got it. Got something. Yeah.
That's why I wanted to, just so that he can proceed with whatever
No,
he.
thanks a lot. Got it. Because I was doing the summations and doing like that, but concept should be clear. No? Like what we are doing exactly. Okay.
Yeah.
Got it. not
Okay,
something.
so what we are saying is we are finding out the probability of observed data, and this data is parameterized by these two values, right? Because we are assuming that this is coming from some distribution. Is that fine? But
Yeah.
again, we have so we have one more condition. Initially, we said that independent, right? So we said that each of these values are independent of each other, right? Observing this data is the independent of each other. So when I say that independent, is this kind of a joint density? Can you look at it like this? So probability of so let us say these are parameters, or these are the random variables x1, x2 to xn, right? And what does this mean by probability of x1 comma x2 comma xn? So what is the probability that uh, getting this random variable at the same time, right?
Yeah.
Is that fine?
Yeah.
So all of these are the random variables x1, x2 to xn. These are the random variables. So
Random and independent.
yeah, so if they are independent, in that case, how will you write the joint density in terms of their product of their marginal density? Is that fine?
Product, yeah. Probability of x1, probability of x2, probability
So
of
it
y.
is like kind of probability of x1,
Yeah. Product of both, all.
right, into probability of x2, and like that to into probability of x3, right? Okay, is that fine? So if you think about it, it is nothing but the probability of this random variable, right? So it is like, what is the probability here? It is e to the power, or maybe 1 upon root 2
1
pi
upon
sigma
sigma root 2 pi e
uh,
to the power minus half
or okay,
x minus mu
maybe I
of
can say x minus
divided.
mu
Hmm.
square by 2 sigma square into 1
Yes.
upon root 2 pi sigma
No, already there.
to the power
Yeah.
minus
Yeah.
x2.
Yeah.
Here it will be,
Yeah.
change will be x2, right? By sigma square upon 2 sigma square, and like that 1 upon root 2 pi sigma e to the power minus xn minus, sorry, this is xn minus mu square upon 2 sigma square, right? So if I just found out in a compact way, how should I write it? Product of I equals to 1 to n. What is this?
1 to n. 1 upon sigma.
Can I say that
Yeah.
root 2 pi to the power n
Yeah. It will common.
sigma to the power n again, right?
Yeah.
Into e to the power, what will be here?
Summation of this
I equals to 1 to n,
1 to n.
maybe
X
xi,
I minus mu I, no, mu.
right? Is that fine?
To sigma. Yes. 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 E to the power
uh,
minus
right, this is what, this is called as a likelihood uh,
likelihood.
of what?
Likelihood function of the
So
this
likelihood of this,
Normal distribution, mu
or
and
I
mu
can
by
say,
sigma square.
yeah,
likelihood is this function. Yeah.
for observed data, right? So whatever the data is there, okay, is that fine? So now what next? I wanted to maximize this likelihood, right? To, because
This
we
is the
wanted,
likelihood of this data and this parameter. What you have assumed. Is it?
it is the so
Likelihood is a function. Likelihood is a function. No?
this is the function, right? Whatever we
Yeah.
are getting is
And
the
this
function.
function, the having the parameter of data and the mu and sigma square, right?
Yeah, correct.
Correct.
Fine.
No?
Yeah.
Yeah. Okay. Thank you.
So is that fine? So now what we wanted to do, we wanted to maximize this likelihood function, and that is our goal here, right?
That is
So one way to do is what? How to get? So this is the function, right? So anyway, we are saying like all the time that this is a function, right? So you have this function. Suppose you have y equal to or maybe I'll say instead of y, I'll write like f of x equal to, let's say, x square. How to find the max of this function? What is the value of maximum of this function? So generally, how will you do that?
Took the derivative.
Yeah, so generally, so our general, we use the calculus, right? And you just find out its first derivative and equate it to 0, right? And then you'll get, like, let's say x equals to 0, you'll get a critical
yeah.
point, and you after that you take a double derivative to understand whether it is a
whether it is
maximum
maximum or minimum. Yes.
minima, right? But what we are saying here is, okay, I wanted a maximum of this function, right? Or I wanted a maximum of this whatever function we are getting here, likelihood function. What does that mean? What I need to do now? I need to take a derivative, right?
Here we take derivative.
Derivative and equate it to 0. Fine.
Yeah. Yeah.
But again, so this is a derivative of the products, right?
Yeah.
So let us say if I wanted, and how many variables are here? Currently, how
5.
many variables? Okay, no, not 5.
No. 3.
No, what 3? No.
Okay. No. That the mu and sigma are the fixed.
Okay,
Only one.
what is x1, x2? We know, right? We know all these values, right? x1, x2 to xn. These are basically these values, right? Is
Two
x1,
variables are the mu and
x2,
sigma.
x3, x4. So are we going to differentiate with respect to these two, or we are what is unknown here?
Mu and sigma.
Mu and sigma are unknowns,
mu
right?
and sigma square.
These are the unknowns,
Yes.
right? So that means it is a function of two variables. Is that fine? Right
Yeah.
now?
Yeah.
So how do you do this maximization or minimization using the calculus if you have two variables? Partial derivative with respect to one,
Pass.
and
Yeah.
keeping other variable as constant. Is
Other
that fine?
constant. Yes.
That is
Yes.
what. So if I have a multiplication here, let us say uh, you have like, okay, just like, I'm just giving you the example of like this. Let's say x square y. Okay, how many variables do you have here? Two variables, right? And if I wanted to find out its maxima, what should I do, or minima? What should I do? I need to find out its uh,
df upon
sorry,
dx.
dx
df upon dx
to
with
0,
respect to
and
x. Yeah.
sorry, like, okay, like this, or dy equal to 0, right? But in this case, what happens here is, since it is multiplication, right? Or these two are actually, these two variables are multiplying, and okay, here it's a simple case, you have like x square into y only, right? But if you have the complicated function like this, right? So you can't be able to eliminate other values, right? Possibly. So okay, general thing to know here is, taking a derivative of a product is little bit it's not like you'll not be able to do it. You can be able to do it right now also. If you wanted to, you can do it easily. But taking the derivative of a product, right, is much harder than compared to taking the derivative of
Addition, subtractions.
addition side, yeah, or subtraction, whatever. So that's why what we do generally here, to take the log of likelihood, right? Okay, I'm just, theta is like all the parameters. Okay, theta will be, let's say, mu and sigma square and your data. What you do then, you take the log, and that when you take a log, it this product sign will become what? The summation. And I think all of you know, right? Like, okay, this is the monotonic function and all that. Okay, that I think
Yeah.
you guys know that. So how it will look like? So this first quantity will be 1 upon sigma to the power n. No, not everything is constant, right? Sigma is the variable here. So first will be like some constant. I shouldn't write that constant, because why? Afterwards, I'm going to take a derivative for this. But if I wanted to write, how will I write? It will be like this. I think it is minus n by 2 log of 2 pi, okay, minus n log sigma plus, or not plus, rather it will be minus, okay, minus summation of I equals to okay, minus 1 upon 2 sigma square summation I equals to 1 to n xi minus mu. Okay, possibly 2 will get cancelled, right? Is that fine? Is fine for this quantity?
Yes.
Okay. Okay, so this is my log likelihood function, and now I wanted to maximize this. So what will be the maximum of this log likelihood? So let us say this is h of x
Mu is equal to 0.
theta, and it will be like, okay, first of all you'll do like uh, with respect to y. Okay, so dh by du mu equal to
Mu.
0, and that will, okay, I'm just solving it, but you, if you understand it like properly, that's fine. So it is like, what will be the case? So this will become 0. First thing is 0. Second term, it will also become 0, right? Because
Yeah.
it is a function of sigma, and we
Yeah.
are
One third.
treating sigma as constant because we are just differentiating with respect to mu. And the third term will be what? Minus 1 upon sigma square.
Minus 1 upon sigma square.
Huh. What is it? Okay, how? Okay, what the expansion of this term will be like this, no? X1 minus mu plus x2 minus mu plus 3 minus mu or something like that, right? Is that correct?
Yeah.
And what will be the differentiation? Yes. Any issues here?
Minus 1.
Plus.
Here any issue when I take a logarithmic log of this part, is that
I do not have any issues, sir.
huh?
I do not have any issues.
I think square term will be here. Square term will not go away, right? If you think about this, so xi minus mu to the whole square, right? Since it is a square of a sum of square of like all the terms, right? It is kind of x1 minus mu whole square plus x2 minus mu whole square plus x3 minus mu whole square. So if I take a log of e, right? So I think that that term will be there. Is that correct? Yeah, I think this. And now I think this will be like this. So what will be the differentiation with respect to mu here? So for this term, it will be 2 times x1 minus mu.
Okay, x1 minus mu minus
So
1.
it is minus, right?
Minus 1.
Minus 2.
Here
Minus 2.
minus 2 x2
Minus
minus
2
mu
x2 minus mu.
minus 2 x3 minus mu, like that, right?
Yeah.
So what does that mean? Eventually, it will, if I take minus 2 common here, what I'll get? Minus 2 will be common. And in the compact term, can I write summation of I equals to 1 to n xi minus mu?
xi minus mu.
Is that okay? If I
Yeah.
take minus 2 as common, the terms will be like this, no? So minus 2 is common, so it will be plus x3 minus mu, like this, right? So x1 minus
Yeah.
mu.
Yeah.
Is that fine? So can I say that it will be like this? Okay, I think you have 2 sigma square here and into 2 times summation of I equals to 1 to n xi minus mu. Is that fine? And that
Minus 2. Minus 2. No?
okay, minus 2 is fine. Okay. That is
Yeah.
anyway the constant. So
Yeah. 1 by sigma square, correct.
so what does that mean again? Right. So okay, for what parameter we are estimating here? Mu, right?
Yeah.
Yes.
So what can I get here? So I can get here like this, summation of I equals to 1 to n
X I minus mu.
xi minus mu. That's it.
Yeah. Ph/du.
Right, equal to 0. Is that fine? Okay.
Yeah.
But now again I'll expand it. Okay, so x1 minus mu,
1 upon sigma square also, yeah, that is 0.
x2 minus mu, like that, right? So if I don't use this bracket terms, what I'll get? Can I write like this? x1 minus mu plus x2 minus mu plus x3 minus mu plus like this, right?
Yeah.
So minus mu minus mu minus mu. How many times minus mu?
Yeah. Mu is equal to x1 to xn divided by n, right?
Is that okay?
Yeah.
So if I can write it down, so it will be summation of I equal to 1 to n xi equals to n mu. and which gives me mu as summation of
Yes.
I equal to
Yes.
1 to n
I divided by n.
divided by n. So that is the, what is this?
Mean.
Sample mean. Sample mean, right?
Sorry.
These exercises are the samples, right?
Hmm.
So whatever the values we are getting for this sample, if I take the mean of that, what we are saying is, by using the maximum likelihood estimator, is that the mean of the, or the population mean of the normal distribution. So what is this? It's not the actual. Okay, what is mu? Mu is the population
Mu is
mean,
the mean of the population.
right? It's a population mean. What is
Hmm.
this mu hat? Mu hat is a
Sample mean.
parameter estimate, right? For, or it,
Parameter.
I can say the estimator for the, or I'll write in the, because parameter is the population mean, so it is a estimator
Yeah.
for
Yeah.
population mean, right?
Yeah.
And from the maximum likelihood estimator, that method, what we have observed is, or what we are concluded is that the good estimator for the population mean is the sample mean. Is that okay? Is
Yeah.
that
Yeah.
fine?
Okay. Okay.
This is a sample mean, right? Okay, so I'll say that sample mean is this. So actual mean is what? This mu, right? Actual mean means the population mean is mu, but we do not have any information about that population mean. We use the method of maximum likelihood estimator to calculate the, or to estimate the population mean by using what? The samples given to me, right? Or the
This
observed data.
estimator, this estimator mean
So yeah.
mu hat
Hmm.
is the our guess. Okay, on
Yes,
based on this method.
method,
Right.
right?
Right. Okay.
Correct. So this is like a scientific method to do it, right? One of the scientific methods to do it. Like
Correct.
instead of just doing a guess, right? We have come up with something, and I think that is better one, right? So if you have some samples, take a mean of that, and you just say that, okay, this mean, the sample mean, might be the mean of the actual population. That is what we are trying to say using the uh, using the maximum likelihood estimator. Fine. You can do it for sigma square. In that case, what you should do is, you should do it for the del h of theta with respect to del sigma square and equated to 0, treating mu as constant. You will get that value as well. Okay.
Yes. Yeah.
So the point to make here is,
But sir,
yeah.
so why sir assume that this variance is known?
What?
Lectures, sir
Huh.
only calculated the estimator for mu only, not for variance sigma square. He
It is
assumes
there.
that it is given.
No, which thing you are talking about?
So the same.
Okay, is there any example given there? Okay, it's okay.
No
I think,
example.
okay, I think it is there already. Okay, fine. Some example is there, but it's okay. It doesn't matter. So here you're just saying that you know that parameter sigma square, right?
Yeah.
But if I don't know, if both the quantities are unknown, in that case, what you should do, right? So not most of the times you know that the variance also, right? In that case, what we'll do, and the answer to this is like the sigma square. If you remember from your uh, stats, right? It is coming as the uh, sample variance only. Okay, the summation of I equals to 1 to n upon 1. This will be, so this is the estimator for sigma square. Is that fine?
So here we are assuming both are unknown.
Unknown, yes. If I know any quantity known, then I'll just go for only the second,
The
which is the
unknown.
unknown one, right? Generally, this estimation, parameter estimation, we do for what? Unknown quantities, not for the known ones. If I know, it's good, right? Then my work will be lesser, right?
Okay.
Okay, fine. Okay. There is another method which is called as the Bayesian estimator.
You were about to make a point before
Sure.
she interrupted you. Can
What?
you please say what you wanted to tell us?
Okay, I forgot. I don't know.
I know. Sanya, no, she interrupted you.
Yeah, yeah.
You said that when you wrote the dH0 by d square delta square,
Huh?
you said that the point to be noted is.
Okay, I think I just
I
don't.
just wanted to pick up on your thought of
Yeah, I
thought.
got it. But I just forgot. Like I don't know.
I know. I mean,
But I think I was talking about that time you treat that mu as constant,
which
right?
one? Sorry.
The mu as constant.
Okay, okay. But
But
what you wanted to say is,
yeah, I think I was talking about this. You treat mu as constant and then differentiate with respect to sigma square. Another thing is
okay, are you trying to make the point that sigma depends on mu, whereas the mu does not depend on sigma?
uh,
That's a fact.
that
Okay.
you can say, but
Mu
because yeah,
no,
that is true, right? Because you wanted that mu to get that variance, right?
no. Let me explain. Let me probably elaborate on what I'm thinking.
Okay, okay.
Mu is a property of the data set.
Hmm.
So mu depends on the data.
Why not the sigma square is not dependent on data?
No, that's later on. That is the second order. See,
Huh. Okay,
unless,
okay.
unless mu is assumed,
Hmm.
sigma doesn't exist.
Okay, that's true.
For a given mu, there is a sigma.
Correct, that's true.
So that is why we stepwise we first estimate mu, and assuming the mu, we can go for the sigma, because the sigma is depending on mu.
Right, that's true.
This is, I would say, I mean, in terms of the complexity, if I
Yeah, that's true. So, because you
see
just
billions of data,
right.
the first thing I can derive is only the mu. I
Right.
can't derive the sigmas.
Right, and it is again, it is
That is a
order wise also is correct, right? Like if you
terms of order, it is a second order,
yes,
or it is like a second order differentiation, or it is a
not second order differentiation also you can think about, like, but it is like mu is like it's a first. So if you know that method of movements,
rate of change, all those
correct,
things. It will come up. It's a second momentum.
right? Second moment,
First
yes,
momentum is your mu. Second momentum is sigma. Third is probably the q.
yeah,
Things
it
like
is
that.
jerk and all that will come in.
That is how you build to probably describe the pattern more accurately. Correct?
That's right. And one more thing
This
to
thing,
note here is this
yeah,
mu you are using, right? It will
yeah.
be your mu hat. So
Mu
it
hat.
will be like
You are right.
estimator. We have already calculated above,
And that
right?
is what I was expecting you to say, so that people get
Yeah,
clarity.
that
Right?
is true. That is true. Yeah.
Good, good. Anyway, she disturbed, and
No,
that's
that's
all.
it.
That's all. Go
Okay.
ahead.
So I think okay, the second point I wanted to make about, yeah, I think we were discussing about Bayesian estimate, right? So Bayesian,
Yes.
yeah. I hope these things are clear. What is maximum likelihood and maximum likelihood estimator? What we are going to do here, right? Uh, so this is again similar approach, right, as that of the maximum likelihood approach, because here also we use the maximum likelihood, or we are going to maximize the likelihood function. But the difference here in the Bayesian estimation is that you know something about the data in prior. What does that mean? Let us say you are a manufacturing company and you manufacture the nut and bolts. Fine, you have a sample of nut and bolts manufactured, and I don't know whether you guys are familiar with the terminology of tolerances. If you are, I think it's good. If you are not, it's fine. It's not a problem, right? So tolerance means whenever you have your nut and bolt, right, the size of the nut and bolt should be within the permissible limit. It should not cross that limit. Why? Because then it will not fit, right? The fit will not be there if you know the nut and bolt thing. So I think so. This is kind of right. So one of the thing is nut and maybe another is bolt, right? So you wanted to insert that nut into the bolt. Is that fine? In that case, if your the diameter of this, right, if it is more, right, what will happen then? Then your hole in the then what will happen? It will not fit, right? So the fit will not be there, and that's why. But is it possible to get the exact diameter every time you manufacture? No, right? You will get like different diameters, maybe some millimeters here and there. So sometimes, let's say you have the diameter of 15 mm, right? 15 mm, then we'll have, let's say, 15.1 mm, then 15 point, let's say, 0.5 mm, or maybe 14.95 mm. There is some, but do we allow all the nuts or bolts to be produced, or do we have something about or some restrictions about it, like how many, let us say, if I say that it is, I can take plus or minus, let's say, 0.05 mm. What does that mean? I can allow this diameter, I cannot allow this one, I can allow this, I can allow this, right? So you'll have to reject some of the nut and bolts, right? So that kind of thing will be there, and generally it follows the normal distribution. But the point to note here is that how we can say, so if you'll have a sample, right? Let's say you have 100 samples of nut and bolts with you. So how will you say that this is going to be, or how can we set the permissible limit here, right? To do that, maybe you can use the maximum likelihood estimator and try to find out the parameters of that, right? Because what I'm saying is, whatever, let us say this is the error, right? This is the error. Error follows the Gaussian distribution. If I assume that, okay, then how can I set the parameters for this, right? Because the population would be what here? Population would be all the nut and bolts, or let's say not, don't worry about nuts. Let's say we think about bolts. All the bolts produced in the manufacturing unit, right? That will be your population. But now again, see, it is a difficulty. We cannot have measured all the bolts produced, right? Because it will be huge quantity. In that case, what we use is, we take 100 bolts, which is sample, right, and try to get the answers for this, the mean of the distribution and the sigma square of the distribution. But let us say one employee is there and he is working for, let's say, 20 years, okay, in the same company. Over the years, he might have got some understanding of this distribution, fine, because he is seeing, like, maybe in the nuts produced, like, in a bulk, right? So much of large quantities he is able to see that, and now he has some assumption about that mu and sigma square, fine. Is that okay? Right, so he can say that, okay, mu might be, let's say, 0.5 mm, okay, or maybe I don't know, maybe
On the basis of his experience, he is assuming,
yeah,
right?
he can say that, okay, whatever I observed, the distribution is Gaussian, and its parameters might be 0.05 and sigma square might be, I don't know, maybe again 0.05 mm square, let us say, fine. Is that okay? Now, with this information and with the sample in your hand, so you have taken the sample of, let's say, x1, x2 to x100, okay, you have 100 bolts in your hand. Now you have exact values, right? Now x1, x2, x100 means what? I have the exact value of the diameter or whatever the errors, right? Let us say these are the errors. So whatever the errors, these are the exact values I am having. Now with this errors and with the information given by that experienced person, fine, can I come up with some better estimator for this parameter? Is that fine? So what I'm saying, that this x1, x2, x100 are coming from some normal distribution with parameter mu and sigma square as the population parameters, and also I have additional information about what, this mu and sigma square, fine. It might be a constant value or it might be a variable one, okay. So what does that mean? I'll try to explain it here. Maybe I'll take a simple example. I hope this example you kind of get it. Let us say you have x1, x2 to x100. They are coming from Bernoulli distribution. Right? This is a different example with probability of success p. But I have some information about this p, and what I'm saying that this p is not a constant. Okay. Previously we thought that this is a constant, but now we are saying that this is not a constant now. This is some variable. Fine. So the parameter here, we are saying that it is not constant, it is some variable. Now if it is a variable, if any, or maybe say I'll say that random variable, and if it is a random variable, then it will have what? Some distribution associated with it. Let us say it is generally, again I can say it is Bernoulli also, but let's say it is beta with some values alpha and beta. Is that fine? Right? Okay, so this p is not a constant, this p is some variable. Now according to a Bayesian estimator or Bayesian distribution,
This is Bernoulli.
yeah, because for simplicity I'm not taking this normal distribution for now.
Okay, you're just assuming that is the Bernoulli.
Yeah, some Bernoulli distribution. It is some different problem. I have given that problem for the context, but now you just think about this is some problem, some other problem. Let us say these samples are
different from the previous one. Yeah.
So these are some samples coming from Bernoulli distribution, and this Bernoulli distribution or this parameter, right? It will have some other distribution with and that parameter is having some distribution with and that distribution is beta distribution with parameters alpha and beta. But these are the known parameters. Is that fine? Known parameters. Why they are known parameters? Because this is based on some experience, right? Prior experience. So is that okay?
And what is beta? Beta is also a distribution.
Beta is a distribution of your unknown parameter. Yeah.
Okay.
What we are saying is that I have some information about this.
Beta is a known distribution which is having alpha and beta parameters, right?
Correct. But what kind of distribution it is? It is a distribution of p, right? In this case, the probability of success. Okay.
P, yes.
And what this Bernoulli distribution is?
It's the sample.
It is a distribution of a
sample.
Yeah, you can say that, and it will have some probability distribution p. Okay, is that fine? And this is, let's say, okay, sorry, I just did not mention this IID distribution. So if, let us say, don't worry about this for now. What will be the likelihood for this? Likelihood of p given some this data x1 and x2 to x100. The likelihood will be what? The product of 1 to n, and let us say among this 100 you have, let's say, 60 as the you get like 60 p's and 40 what does that mean? 60 successes and 40 failures. Is that fine? In that case, what will be this product, or what will be the likelihood? Likelihood will be p to the power 60 and 1 minus p to the power 40. Is that fine? Okay. But okay, I think all of you know the Bayesian Bayes rule, right? What does the Bayes rule is?
Probability given of probability of A given B. A of yeah.
Probability of A intersection
probability of A intersection B.
A intersection B upon
A intersection B.
Okay, let us say okay, and
probability of B,
right,
multiplied with,
not to multiply. This is okay. This is conditional probability, right? Generally, the Bayes rule is the extension of conditional probability only. In that case, this probability of B will be what then? It will be like let us say if you have more than one events, right? In that case, okay, we just talked about one event here. Let us say you have more than one events, then it will be what summation of all this, right? Probability of I don't okay. I hope you know this, right? I don't want to explicitly. Okay, in this case, it is like very clear. Let us say x1 to x100, right? You have like this many events and this p, right? Okay. In this case, maybe I'll write down for this. Let's say product of P given, let's say x1 to x100. So it is not like 1, right? So what will be the condition probability here for this? Or let's say with respect to x1, what will be it? All of you know the Bayes rule, right?
Yes, sir.
Okay, then I'll not. Maybe you can just see it later, right? Already we are running out of time, so it's fine. Okay, it's not that easy. It's not that difficult. Maybe I'll just show you the diagram. You can just think about it later on. So you have like independent events. Okay, let's say you have A1, A1, A2, A3, and let's say AN events, and you have one event which is common among all. Uh, let's say that it is event B. Then what is the probability of B given A1, right? So in that case, you'll get that Bayes rule, right? Okay. But okay, in this case, what I was saying is this probability will be equals to probability of, okay, maybe I can say that probability of uh, probability of, let's say, in this case it will be, maybe I can say the probability of P, probability of let's say x1, x2 to x100, right, divided by, let's say, P, and this kind of, probability of B given A divided by probability of x1, x100. Is that fine? Is that okay? Into, is that fine?
Yes.
Yes, sir.
I think let's say what of A given B is probability of A intersection B and probability of B. Fine. And let us say probability of A intersection B is what? Probability of B given A,
A
probability
into
of A
probability of A.
divided by probability of B, right?
B. Yes, yes.
That's fine.
Yes.
And this is what it is. Like this probability. So probability of P given, let's say, x1 to x100, it is just probability of, okay, this is one event, right? This event A and this is event B. So it is probability of event B given A, right? Is that fine? Into probability of A and divided by probability of B. Is that fine? Okay.
Yes.
Is it analogous? Okay.
Yeah.
In this case, this term, the numerical, sorry, numerator term, it is called as the likelihood, and this term is called as the prior, because what is this probability of P? This one, right? It comes from the beta distribution. That means it
Known.
comes from
This is known one.
known, or this is based on your prior experience, and that's why we called as uh, the prior. And actually this is a, okay, and this will be a constant, right? Everywhere, every time it will be constant, right? Because this
Sir, which one?
the denominator one, probability of x1 to x100 is constant. Why it is constant? Because, okay, can you tell me about this? Let's say okay, so what is the probability of A1 given B from this diagram? What is this probability of A1 given B?
Probability of A1 intersection B divided by probability of B.
A intersection B
Probability of
upon
Probability of
B.
B.
Uh, in other words, can I say it is probability of
Probability of B given
given
A1
A1 into probability of A1
into A1 divided by
divided by
probability of B.
probability of B. But what is probability of B? Basically,
Probability of
if you
B.
think about this, it will be the probability of this plus this plus this plus this, right?
Yes, yes.
I would like to add something, sir. As means, if I remember, it was probability. Probability of B was equal to probability of A intersection B plus probability of A intersection B
Correct.
complement.
Complement.
Yeah, I mean, it will include the area of where A is intersecting B and also the complementing area, like the area which does not include A. I mean, we will take the whole of B.
No, probability of B basically. So what is B event, which is intersecting everyone, right? This is the B event, right?
Yes, sir.
So when I say probability of B, what does that mean? Is inherently it is this part, right?
Oh, yes, sir. It is this
Correct.
one. Yeah, yes.
So it does not include complement. It's simply it is like this. Okay, I'll tell you what is this. Product of B into B given A1 and into product of A1 and divided by what is product of B here is probability of, can I say that it's kind of probability of what this portion is? This portion is the shaded one. This is probability of
A complement.
no A1 intersection B. It's A1's
Yeah,
intersection with B, right?
Yes.
Correct?
yeah, yeah. A1 intersection B,
That's it.
correct.
This portion is probability of A2 intersection B, right?
Yeah, yeah. A2, A3, right.
So can I say that it is A1 intersection B plus or is that it?
Yeah, yeah.
Yes. Okay, product of A2 intersection B and like that, right? So
Hmm.
further, if you try to be okay, product of A1 and divided by product of A1 intersection B is what can I write here? Can I write it is product of B given A1 into probability of A1?
Mm-hmm.
This part can I say it is product of B given A2 into product of
Into
A2
probability A2.
and like that, right? So when I what is this probability then? Probability of A1 given B. Is that fine? Right?
Yeah, yeah.
Okay. Now, if I wanted to find product of A2 given B, what will change in the above part? The change will be here.
A1 will come
A2,
into A2,
here
A2.
A2. Will there be any change in the denominator?
No, denominator will be
No,
same.
So that means this value is constant irrespective of whatever probability you're trying to find it out, right?
Hmm.
Is that fine?
Correct.
And
Fine.
similarly, if I wanted to say that, okay, I'll just write it down here again because it becomes messy. So if by using the Bayesian estimator, right, or if I try to use the Bayes rule here for likelihood function, it will be kind of like this. Okay, just let me see once. Okay, this is the probability of uh, okay, probability of what is it? X1, X2 to X100, right? Given what? P, that parameter into product of P. Is that fine? Divided by, I think I'm writing this right. Okay, divided by probability of X1 to X100. But we already have seen this. This might be a constant, right? Or this is going to be constant, right? So then this likelihood function of parameter when we observe with respect to the data, uh, what this will be then? If this is constant, can I write in terms of the proportionality sign? So it will be proportional to what? Probability of x1 to x100 given p into probability of p. Is that fine?
Yeah.
And okay, and this is what your likelihood function is, or likelihood is called likelihood, is called prior. So you're
Right.
adding this prior function to it, and now by looking at it, right, then you will try to find out uh, the estimator for it. Okay, now what next? So I'll just continue this example from the that coin toss, right? So we observed like how many
What is
six
on the LHS? LHS is also likelihood, na?
likelihood, yeah, likelihood only.
LHS on the LHS.
Yes,
Go down, go down. Yeah,
likelihood
the
means
likelihood into prior. And
basically it is
on,
not likelihood. I'll say it is
what
kind
is
of
this? What is this?
because we already have said likelihood into prior, right? So it is not likelihood. Basically, it is a probability. It's basically a probability of
The probability
p
of
given
what?
p given x1, right? we were started with this, no?
Oh, yeah. Okay.
Right. So
Okay. This is another function which is a product of this likelihood and prior. Right?
likelihood and prior, yeah.
Okay.
Right. And now if I just use for that Bernoulli trial, so it was like p to the power 60, and what is it? 1 minus p to the power, let's say 40, and we
40.
said that that was a beta prior, and let's say the parameters
Alpha
are
beta.
maybe 10 and 5. I don't know what exactly are, but what will be then? It's like p to the power 10 and 1 minus p to the power 5, I think. Or sorry, I think it will be 9 and it will be 4, right?
This
think,
prior will be given in the
yes,
question
yes,
also, right? Okay.
because that is known to me, right?
Mm-hmm.
Okay, in this case, then we'll just try to solve it, and it will become 69 and 1 minus p to the power 44.
44.
And now the estimator for the parameter, because we are interested in the estimator of the parameter, and that will be your, you can use the mode or something. This is called as actually a posterior density. I hope you have remembered this posterior density, right? So this is probability of p given x. This probability is called as the posterior density. Okay. Okay, so the posterior mean, some generally people use posterior mean. They can use posterior mode or something like that. But let's say posterior mean will be what? This probability density function looks like what? Beta, right? Beta density.
Beta.
And in that case, so beta with what? Alpha as I think 70 and beta as 45.
45.
45.
And I think the posterior mean is, I think, alpha upon alpha plus beta. So alpha will be
70.
so something like that, 70 by 115, and that will be my estimator for what? This is going to be the estimator for p, right? If it was only likelihood function, what we have would have achieved, it might be, I think it is 60 by 100, which is 0.6, right? Only likelihood, fine. But with the prior knowledge, we have come to some other number. I think this number is 70 by 115. You just calculate it. It is not 0.6, definitely. It is more than that, and or not more than that. It's different than that. So it is, I think, 70 divided by 115. It is 0.6086.
We are
So
integrating here our present calculation or estimation with the prior already
yes,
known right. We are integrating both, right?
right. Right? And that's how it is different for it is different from Bayesian estimate. I think it's fine. Oh, sorry, MLE. Just give me a minute. I'll just
And
come back.
it is assumed to be more better than that, right?
No, it's not like that. It depends. See, it's not about more
Okay.
better or something. If you
Okay.
don't have the information, let us say you
Okay.
don't have any prior information. What do? You can't use Bayesian estimator, right?
Can I give a different perspective for whatever we
Yeah,
discussed?
yeah. You can give it. I'll just come back in 2 minutes.
Yeah,
You can
that's
maybe
okay.
you can continue.
That's okay. Srikanth,
Yeah, please.
yeah,
Please.
let's assume two scenarios.
Yeah.
Say there is a bunch of youngsters, okay? Like you and me were not there, a part of the team. Only 20-year kids. They were there to analyze some data. They were supposed to analyze some data, right? They have observed and they made a survey and then they made some estimation. They assume some pattern. Okay.
Yeah.
We were not there in the team. It's only the youngsters, right? They made an assumption it could be a Bernoulli or whatever normal. Based on that, they make estimation from what they can observe, right?
Based on the sample data.
Observe data. So they make an assumption it is a Bernoulli, they make a parameter assumption, and then try to find the maximum possibility that observed data can match. Okay? So that is your ML estimation. So it has no prior knowledge. Now, second scenario is people like you, Srikanth, with 50 years experience. You become a part of it. You come in and say, oh, in my experience, this data has a probable distribution like this. Correct?
Yeah.
That is a prior knowledge, which did not exist in MLE. In MLE, the youngsters don't have a prior knowledge. With the experienced person, consultant like you joining, you have a prior knowledge, but that was a prior knowledge. In addition, we have new data. Correct?
Yes.
How do we combine these two? That is your base.
Bayesian.
In the base estimation, we use the prior knowledge and the observed data to arrive at a combined intelligent estimate. You get it?
Yeah, of course.
That without a prior knowledge, Bay doesn't exist. It's only MLE. With the experienced people like Srikanth, who has 40 years of experience and he knows, hey, this data must have a distribution like this. I think this is the parameter. That is your knowledge. So we can't ignore it. We shouldn't ignore it. But we have to club them together. That's where the Bay comes into play.
That will certainly give some added value.
Correct. Bay is only an incremental intelligence.
Correct.
Okay. I mean, I don't know whether it reaches to.
Everybody, because
This is
your
the
concept is, every time you hear the concept with example, that is the best way to learn.
Yeah.
For the beginners.
This is how intelligence evolves. Okay. I'm not talking to you. I'm actually teaching my daughter. She's in this parallel channel. I'm teaching her. The difference between the two, MLE versus a Bay, is this. MLE is when you have no prior knowledge. A new generation, if we have to collect intelligence, they got to use MLE. If they have the benefit of the old generation, they can take the old generation information and keep improving upon. That is Bay. Okay? You got it, Dalchalo? I'm teaching my daughter. I'm just parallelly propagating to you guys.
Good.
Yeah, she is doing research in ML, AL and all those nonsense. And
she is also doing the same course?
No, not this course. she is in MIT doing some research in advanced AI, and she probably will generate things which you probably will your kids and fine.
Nice.
Thank you.
Concept is very, very clear, and I always get benefited from a concept. Maybe I take some more time, but I always learn from your clarifications. And always you clarify my questions. I always follow you. Whatever time I found. I'm very thankful to you because your concept is very much synchronous to my concept. Because when you clear, I get it very much. Thank you. Sorry, it's W perhaps. Thank you. Okay. So I have taken break or something.
Sorry.
Sir has come or
I think he is preparing something.
Oh, sorry. No. I was speaking. I was on mute. Okay. So I was saying that
let's
move ahead right now. So we understood why this parameter distribution and all are required. Now we'll maybe dive into the algorithm, which we will stick to it right now. So why we need this EM algorithm and what purpose it serves, right? So we already have seen, okay, this is what kind of algorithm we can see. It is unsupervised one, right? Unsupervised algorithm. If you guys have already covered, maybe completed your MLF, you might know that we have learned about mixture of Gaussian or Gaussian mixture models, right? But if it is not, no issues. Let us try to understand. We already have one algorithm for clustering, and what is that algorithm? We have seen earlier. We have seen the k-means clustering, right? We have seen that algorithm previously, which is k-means clustering. And if you remember k-means clustering, what you used to do, you try to find out the distances from the centroids. So you just assume, maybe initially randomly initiate the centroids, and then properly find out you find out the distances from each of the centroid, and you try to allocate the data point into that cluster, right, based on the distances, minimum distances, right? Okay. What do you or what did you do there previously? It was that you hard coded it, right? Or maybe you have already found out, every time you have to find out the distances from each of the centroid, and you'll have to assign the data point to the new centroid, or you have to keep the data point into the existed centroid or center cluster, right? That was we have done in k-means clustering. And probably the better approach to that was the k-means plus plus. That was also the probabilistic approach, but that was not used for finding out the clusters. That was used for what? What purpose? To get the better initialization
Bayesian.
for the centroids. Is that fine? Right?
Yes, sir.
We wanted to find out the better centroid, and we used a probabilistic approach there. But now, can we find out these clusters probably by using uh, the another way, without the hard clustering, with maybe the term known for the CM algorithm is the soft clustering? Can we be able to do that? That is the question, right? So that means probabilistically, can we do that? So whatever we have learned so far, we have learned about the parameter estimation, right? And what parameter? So we have seen the example of normal distribution, and it what we used to say, the sample which is coming out from it, we are saying that it might be coming from a population which is having a distribution of normal, and it will have some parameters, and we try to estimate those parameters. Is that fine? I think till that part is fine, right?
Yeah, yeah.
Yes, sir.
Okay, so let us say, and why we need that now? Let us say if you have certain data points here, what do you, if you use the maybe the k-means clustering, what clusters you can get it here? Maybe this is one cluster, another
Three
cluster
clusters.
here, and
Three
three
clusters.
clusters,
Yeah.
right? Right. But this is based on what? Maybe, but this is going to be a good cluster anyway, right?
Yeah.
And how you decided those clusters? So probably you have started with, let us say I started randomly with these three centroids, let's say mu1, mu2, and mu3. Fine. And what do? You you calculated the Euclidean distance probably for each of the data point, right, from that centroid, and you do similarly for mu1, mu2, and all the three, and then you change the centroids. Is that fine? And
Yes, sir.
ideally you end up in getting the proper clusters for that. But let us say if I don't want to go with that way, right? Because again, see, every time I need to find out the Euclidean distances, right? Can I assume some probability distribution, and if I say that these data points are coming from the distribution, right? Okay, is it
Pardon,
fine?
pardon once again, sir. What are you telling?
What we are saying is, instead of uh, doing this like every time calculating the distances, can I use some probabilistic way and assume that each of this data point, they belong to some of the distribution? Fine. Each of this data point, fine. And
Yeah.
we say that, okay, if it is coming from the distribution, what is the probability associated with the that data point that it comes from the distribution? Fine. Okay. Let us say this is a sample coming from some known distribution. Fine.
Yeah.
So in real life, we know that like very generally people use this what normal distribution, because if you think about the height of the weight of most of the continuous parameters, I think they will be coming from your normal distribution. But do you feel that this will come from any normal distribution, or this sample is from, like, let us say all of these are the samples, and can you think about that, okay, all these data points are coming from the normal distribution of such. What do you think about that? So what this distribution tells me, that these three data points have the higher probability, right, coming from this distribution compared to these three, right, or and
Yeah.
these three, right? Because if you think about that, the probability here, right, it is lesser than the probability at the middle. So if these three data point we try to find out the probability by using this normal curve, we'll get the higher probabilities for these three, and the probably the lower probabilities to other three sets of three data points. Fine. But maybe this is not a good assumption for this, right? Can we say something else, like can I say that, okay, this is coming from some different, so let us say it these 3 points are having maybe different normal distribution, these three will have different, and these three will have different, some different, right? Is that fine?
Yes.
Yes.
Okay. And what we are saying is they are overlapping to each other at some extent. Okay. Okay, they are overlapping. That means the data point here, if you think about this data point, let's say if you have any data point here, what is the probability associated with this? Or is it the only probability based on this Gaussian distribution, or only from this, or only from this? What do you think about it?
It can be either of this, left or right.
Okay, so what do you think about, so if this is a data point, how will you calculate the probability for this? By using this one, or by using this one, or by using this one? Okay, let's say this is 1, this is 2, and this is 3.
1 and 2.
1 and 2, will it have some component from the third?
No.
Why not? Because if you think about this, it will have slight chance, right? Let us say the normal curve, right? It is always the asymptote.
Very less probability will
That
be
is
there.
okay,
Right?
but it will be having some probability, right?
Yeah.
So
It may.
what I'm trying to convey here is, maybe this point here, it will, like, okay, majorly it will be contributed, let's say, from this, or maybe this, right? I don't know, but some contribution is from this as well, right? Is that fine? So if I pick each of the data point, any data point, let us say this data point, right? So if I wanted to calculate the probability from this distribution, the major contributor will be this one, right? Slightly minor will be this one, and slightly lower from this one. But eventually it will be the addition of the probabilities, right?
Yes.
Or do you agree with me? That's fine, right? So
Yes.
so I should have such kind of distribution, because it is giving me right idea about the data. Is that fine? Because for this data point, definitely it should have some higher probability, right? And is it getting? Yes.
Yeah.
Right.
Yeah.
For this data point, it should have some higher probability, because they belongs to certain. So what we are saying, that all these data points may not be coming from one distribution, it may be coming from different distributions, and each of the distribution actually is contributing something to the data point. Is that fine?
Yes.
So if I wanted to plot a smooth curve about this, right? So let us say this is the sample which is given to me, and maybe this is kind of like this, right? Is that okay? The addition of this, it is not cutting it, but we are just adding it, and maybe that bulge is happening there. So it's kind of like this. Is that fine? It is not. So probably this has to go like this, right? And this has to go like this. So it is kind of a overlap here we are getting, right? And for and this also is somehow it is contributing to that. So maybe this is the perfect perfect distribution for this kind of data, right? So we can assume that maybe my sample, let us say this is sample, right? It is coming from this kind of distribution. Is that okay? Fine.
Yeah.
Previously we had some samples, and we used to say that okay, these samples are coming from my normal distribution with parameter mu and sigma square. Is that fine? Now let us say how many samples are here. Let us say x1, x2 up to x9, right? Nine data points or 9 sample points, and I'm saying that they are coming from IID distribution X with some parameters. Is that fine? And what is this X? So previously we had like this, no,
Prior.
normal, not prior. What distribution is this?
Yeah. This is
called as a mixture of
mixed model.
of
Mixture model.
yeah, Gaussian or Gaussian mixture model or some that.
Gaussian GMM.
Yeah, this is called as the mixture of Gaussians, or GMM is like Gaussian mixture model. Right?
Gaussian mixture model.
So why I'm saying this mixture of Gaussians? Because we are not assuming that this data is coming from normal distribution. What we are saying is it is coming from different Gaussian mixture.
Each cluster can have a different distributions, right?
Right, and that is probably a normal distribution, right? And this is safe to say because in real world, most of the data points, they actually, if you think about the large data points, right, you can assume safely that it is coming from the normal distribution. Okay, that is that clear?
Yeah.
Okay, but okay, another thing here to note is, okay, so let us say here we have three different Gaussians, right? So do they have same parameters? They might or they might not, right? But let us say they are not having. So this might have mu1 sigma 1 square.
Mu1 sigma mu2 mu3, right?
Right, this is mu2 sigma 2 square, and this is mu3 sigma 3 square. Is that fine? So in total, how many parameters we are having here in this mixture of Gaussian models? Six. Assuming that okay, we have only the three different Gaussian curves. Fine. Another part is now we do not have only one; we have more than that. Can we say that each of occurring of each of this, right? Each of this will have some probability associated with it. Okay.
Yeah.
Okay, because every time I'm choosing let's say if I have one data point, what is the probability that I will choose this, right? Or I'll choose this, or I'll choose this. So it will have some probability associated with it, and generally it is denoted by some parameter which is pi1. And let us say how many what do you think, how many Gaussians are here? Are they discrete or are they continuous?
Continuous.
No. Number of uh, normal distributions. So here, how many distributions are there? Normal distribution are there? Three. So are they finite or are they infinite, or are they discrete or continuous? Three is a discrete number, right? Finite. Right. So how many parameters are there? Suppose, so that means, can I say that it is coming from some distribution or discrete distribution, and it is having some parameter? How many parameters it can have? Let us say three, right? In this case, it is three. So assuming that it is some finite parameters, So how many parameters now we are having total in this case? 9.
6.
No, 6 are like this two, right? This two plus this two plus this two. They are 6. Fine. Plus
Right.
plus this one.
Okay.
Pi 1, pi 2, pi 3. So total how many parameters?
9.
9 parameters. Okay. So going forward, okay, let us say instead of that 3, which let us try to generalize this. Let us say you have k clusters, right? K1 or like let's say k equals to 1 to k, fine? Small
Sir,
k.
I think I lost the continuity. What was pi there?
Pi 1 is the probability. Okay, this is a parameter. Like this is a probability that I have chosen this cluster.
Oh, okay.
Okay, so it is kind of a probability of choosing clusters. So if I have 3 clusters, what is the probability that I'll choose the first cluster? What is the probability that? So let us say if I have this data point here, okay, I have to first pick a cluster, right? For this data point. Okay, what is my goal for in this case? If I wanted to do clustering, what is my goal?
But that's okay. I think I got it. Yeah, sorry.
Right. So the goal is to get me
get the highest probability of this.
Yeah. So which cluster it will belong to, right?
Yeah.
So what is the probability
We
that
want to find out the highest probability for which cluster, right?
cluster, right? But then
So that we can put the data point in that cluster,
right? But we have finite clusters, right? Like we have k clusters, and we have seen that in k-means clustering also we have seen that there are like finite clusters. So if I have finite clusters, but then what is the probability that I'll choose the cluster number 1 for this data point? What is the probability that I'll choose the cluster number 2 for this data point, right? So each of whenever I'll choose the cluster, it will have some probability, and that probability is given by this pi 1, pi 2, pi k. But that also is unknown to me, right?
Yeah.
Correct? So how many?
Which is unknown to you? Which is unknown?
This probability, right?
Pi 1, pi 2.
This is also not known to me.
We
Right?
have to find it, right?
Yeah, I have only knowledge of, let's say, number of clusters. Right?
Clusters only, yeah.
And what else I have?
We need to find out this pi 1, pi 2, pi 3, so that we can decide which one is the highest set, right?
Correct. So I have only information about the sample, and I have the information about the number of clusters. Fine, this is known to me. Now, what is unknown to me? What are the exact probabilities for these clusters? Then, if I choose this cluster 1, how many parameters are associated with this? Mu1 and sigma 1 square? 2. Mu2 sigma 2 square. And how many here? Mu k sigma square. Okay, one of the properties of this is the sum of all, right? So pi 1, pi 2 to pi k is equal to 1.
1.
Okay, this is the property. So let us say if I, okay, how many, now all of these are what? Like these are the parameters, right? And they are unknown. Is that fine?
Yes.
These are the unknown parameters. So now, what technique I am having right now to find out or to estimate the parameters? MLE, right?
MLE, maximum likelihood
estimator. Okay. But basically, okay. So how many? So here, how many parameters I need to, estimate for? To get the estimate for. So here, 2 times k. If I'm having k clusters, right?
2 times k. K means
Clusters, right? Clusters, right?
Number of clusters, right?
So each cluster will have 2 parameters. So 2k plus how many these parameters? K?
1k, yeah. 3k.
All right. But one more thing is, if I know that this is pi 1 to pi k equal to 1, right? So if I know k minus 1 parameters there, can I find out?
This 2 plus k, which 2k is 1.
2k is for what? For this 2 plus 2 plus 4.
Yeah.
Right? And k is for what?
K is for
this one, right? These are also unknown, right? Pi 1, pi 2. This probability is also unknown to me, right? Choosing the clusters. Okay, in this case, let us try to understand how many parameters I need to estimate here. This 2, this 2, this 2. How many?
6, 6, 6.
6. Can I say that if the number of clusters are 3, it is 2 for each cluster into 3?
Yeah, correct.
Plus, I don't know this one, pi 1, pi 2, pi 3. How many are there?
3.
3, which is equal to k.
Okay.
So 2 into k plus k, right?
Yeah,
This
number of clusters. K is the number of clusters, correct.
And each of that will have some probability associated with it, right? Okay. Now, but I don't need like all k's here. Why? Because I know that this pi 1, pi 2 to pi k is equal to 1, right? So how many parameters I need to estimate for k minus 1?
K minus 1.
Okay, you can actually find out for k, that is not a problem, but let us say actually in actual scenario I don't need that one extra parameter, because if I have k minus 1, how can I find the kth one?
1 minus.
1 minus
After
all,
just my 1 minus that.
right? And so total how many parameters I need to estimate, need to get the estimate for is like 3k minus
3K
1.
minus 1.
Okay,
Yeah.
that is fine. Okay, until this part is fine.
Yeah.
Okay. Now, now we'll try to understand this part now. What is our goal here now? What we are saying is, we are assuming that our data or our samples are coming from this distribution, right? Is that fine?
Yes.
Okay. Each of this data is coming from this distribution, and now I need to find out the parameters for that. That is my goal, right? So you need to generate this data. The generative story and all, you maybe check it from the lectures. But right now, if you think about the mathematically, what we are trying to say that I think you guys are familiar with this Z notation. Z is what? Cluster indicator, right? Right?
Yeah.
Zi, let's say, and let us say if you
ZI.
have k clusters, so each of these data points will belongs to, so I is what? Let us say data points.
Data.
So they will belong to what? One of the clusters.
One of the clusters.
And how many clusters I am having?
K clusters.
Is that okay? So each Zi belongs to that k clusters. So and what is pi? I said pi 1, pi 2 is what? The
Number of
probability.
clusters.
No, it's not. That
Yeah,
is probability.
the probability of each cluster.
So what is the probability that the cluster indicator for the ith data point is equal to L? Is given by pi L. Okay. And what is L here?
1 to k.
There is a number of clusters.
L is 1 to k.
1 to
Right?
k.
I hope it is fine. This is what actually it's there in the lectures, right? Are you able to understand that? So that means if I pick this point, okay, let us say this x2 is the point. So x2 will belong to cluster 2. Okay, right? So this is cluster 1, C1, C2, and C3. Or can I say that? Okay, I'll say not C. Maybe I'll say that the cluster indicator for the this is 1, right? This 2, is 3. Okay.
Yes.
So what I'm saying is, what is the probability that x2 will belong to cluster 2? It is given by pi 2.
2. Pi 2.
It's like, it's kind of that's in a simplified way, I'm saying that this data point belongs to cluster 2. The probability of this this data point belongs to cluster 2 is given by pi 2. Okay. Mathematically we look write like this. So Zi is the cluster indicator, and that this data point belongs to that cluster is given by pi k. Fine. Okay. Now this is my step 1. And what is step 2? Now I wanted to generate this data points, right? And they will be generated by
This is general formula. P Zi is equal to L is equal to pi L. The probability of Zi belonging to the probability of this is equal to L will have the probability of pi L. This is a general formula, no?
General only. So what I'm saying is, what I'll do is I'll do that. Okay, I have 3 clusters. Okay, Z1,
Yeah,
Z2, Z3. Fine.
Yeah.
I'll say that the probability of Z equals to 1. Okay. So how many K's are here? K equals to 3.
K equals 3.
So I can say that probability of Z equals to 1, the cluster indicator equal to 1, is equal to pi 1. Okay?
Pi 1.
Probability of Z equals to 2 is pi 2.
Pi 2.
And probability of Z equals to 3 is pi 3. Is that okay?
Yeah.
Okay, done. Now I already have defined this. Now what I'll say that I will now I'll generate the data from this. Right? Okay. So now can you tell me that if for any data point, okay, for any data point, let us say this data point x1, I'll say that x1.
Yeah.
So if I have already calculated the cluster indicator for this, so
X1 is any random. X1 is any random data.
Any data. Okay?
Yeah.
Any data point. So x1 belongs to cluster 1. Fine. Let us say x1 belongs to, I said that x1 belongs to cluster 1. With how much probability? Pi 1.
Pi 1.
Okay. Now, if I say that, okay, this data point belongs to that, what is the probability that it will belong to now cluster 1? It's kind of like that. And in that case, since if I fix the cluster, right, cluster indicator for that, after that, it will have, okay, so let us say if this is the cluster 1, what other parameters it will have? Now the data in this cluster, right, is distributed according to the normal, right? Normal, mu1 and sigma 1 square.
Mu1 and sigma 1 square.
So now once I say that, okay, when now I've told that, okay, these are the probabilities for these clusters. Now can I generate the data based on that? So this generation of this data points will be based on the, so what is this?
We are finding the generating the data from the probability, or we are finding the data probability of the data to be fixed in the cluster.
No, we have samples given to me. Okay, I have 9 data points.
We are having data.
Yeah, because finally we wanted to use this MLE, right? What I'm trying to say is, okay, leave about all of this. Let us try to say that how many parameters I need to estimate now. The cluster indicators, right, or probabilities of cluster indicators, and then each of the cluster, right, it is generated from that Gaussian distributions. Fine. So total of 3k minus 1 we needed. Then
3k minus.
Okay. Maybe I'll come to that generation part later on. What to do now? What to do now? If I wanted to find this, I know that I'll have to use maximum likelihood estimator. Fine.
Yeah. First we need to pi 1, pi 2, pi 3, and
not first, like everything, like at the same time
everything.
You can get it, right? So let us say you have pi 1, pi 2 up to
pi k,
maybe pi k or pi k minus 1. That's fine. Then you can have mu1,
sigma 1, mu1, mu2, mu k,
and
sigma
1
1, sigma 2, sigma k
square, and up to sigma k square, and given the data.
x1 data, x data, yes.
Okay, or x, or maybe I can
d
x,
d,
or I can say x1 to xn. Is that fine?
xn, yes.
These are the samples. So given the sample, I wanted to estimate the parameters, all of these parameters. So what does my maximum likelihood estimate says to me? I need to get a product, right? Product from I equal to 1 to n, right?
Yes.
And the joint density for Gaussian mixture model, right? Xi, right? So what do you do generally? You get the probability density function, right? You just multiply these probabilities, right? using the probability distribution function. By k to k and sigma 1 square to no square. Is that fine? Is that okay?
Yeah.
Yes.
But I think if you recall from stats 2, there was Gaussian mixture model we have actually seen there also. The concept of, I think, have you seen the joint densities of two numerical variables, the joint densities of two
Yes, sir.
discrete variables? There was one more joint density we have learned, which was the joint density of one discrete and one numerical variable, right? I don't know whether you remember it.
Yeah, I
It
remember
was
the
like
heading.
Right,
it
no?
was
And that density actually looks like this, right? Uh, how we can say that it is one discrete variable, right? And one, I think, one numerical variable, right? Not numerical or
Discrete and
continuous.
numerical are they same?
Huh? Yeah, they are same. They are same. I'll maybe I'll just you know tell you. So how was that? Let us say you have x as a discrete variable, right? And I think y you have the continuous variable. Fine. How that problem was, if you recall, it was x. So x belongs to, let's say, x will have, like, say, 3, 1, 2, and 3. Okay, and let's say it is uniformly distributed. What is the probability of uniform distribution? Or, like, this is a random variable with probabilities 1 by 3, 1 by 3, 1 by 3. And what other information I have? Y given x equal to 1 is normally distributed with some, let's say, mu1 and sigma 1 square. I think, I hope you have remembered this. Is that fine?
Yeah.
What does that mean? If I have x equal to 1, then how this y is distributed? It is distributed according to normal with mean mu1 and variance sigma 1 square. If I choose x equal to 2, it will be like this, right? So the question used to be like this, right? So what is the probability that uh, I think it was like this. Uh, I think x1 equal to maybe 1 given y, something like that. I think, if I'm not mistaken, it is kind of like that, and it was the probability used to be like this: probability of y given x equal to 1 into probability of x equal to 1, right? Plus probability of pi given x equal to 2 into probability of x equal to 2. I think something was something. I'm just maybe. Oh no, sorry,
It
sorry.
is like that. We have
It
to
was not like
get
that. It was like probability of y equal to, I think, let's say 5 or something, right? I can say that. Let's say I'll use a proper notation possibly. Y, and y, and say y equals to small y. Is that okay? Okay.
yes, sir.
And into probability of x2 plus probability of y equals to small y, let us say given x equal to 3 into probability of x3. This is nothing but like, kind of, you can think of this as total probability. Is that fine? Because I wanted to find what is the probability that this y will equal to small y. Then how will you find it out?
given this is given that x is equal to 1 and given the
Because
2.
we have this information, right? We have that, how I know that how x is distributed, but I do not know
We
how
are
y is
adding the
distributed.
conditional probabilities, right? Conditional
Right.
probabilities we are adding
Yeah,
separately.
yeah, then only I'll get this y, right?
Yeah.
Because this y is dependent on these three things, right?
X1, X2,
how,
X2 both.
yeah, how you are choosing this, right? And that distribution actually was looking like this gmm. If I don't know if you guys have forgotten, you may go through that lecture again, but this was the case. Is that fine? And this same,
In stat 2, the previous
yeah,
one.
stat suit is there, in MLF also is there, but MLF it is differently explained. why I'm showing this to you, the reason for this is, if I wanted to write down this complexly or compactly, not complexly, compactly, how will I write this? Can I say that it is summation of, or can I say that it is a product of I equal to 1 to 3 and summation of I equal to 1 to maybe, I don't know, or let's say some different variable k equal to, let's say, 1 to 3, let's say, and can I say that it's probability of y equals to small y given x equal to k. Into, let's say, oh sorry, into probability that x equal to k.
It is product of the summation or summation of the product.
You think about this, no? What is this?
Summation of the product.
What is this? This product?
This is product.
And so, and what are you doing? You are summing all the products, right?
Yeah, so summation should be in the beginning.
Yeah, sorry. Okay, I think
summation should be in the beginning.
Yeah. So, okay, that's my mistake. So it should be like
summation of,
yeah. I think in this case, if I have written the product explicitly, so is that fine? Maybe.
Yeah. And product of this. Yeah, okay, it is okay.
This is fine?
Yeah, this is fine.
Is that okay?
Yes.
Yeah, it is okay.
Yeah, this looks good. Earlier, pi was a bit confusing.
Right. Yeah, sorry.
Confusing. You know, I think.
No, this is not confusing, right? This is
what notation. It should be equal to xi, na?
Xi equal to I, right? Okay. How many?
Should we use k?
It should be, I think.
Okay, maybe I'll write
given
the,
xi.
Okay. I will write down in the product and summation form.
Yeah. It is better to write in that first.
Okay, so let us say it is kind of like this. Let us say it is a sum of, okay, maybe k equal to 1 to 3. Is that fine?
Yeah.
Into, let's say, probability that x equal to k, right? Because we have only 3 clusters, right? Three examples here, right? 1 to 3, right? This random variable x can take only 3 values.
Yeah.
Into what? Probability that y equal to y given x equal to k. Is that fine?
Yeah.
Now there is no confusion here.
Yeah. Okay.
Yeah.
Okay. But what is this? Is a normal density. Right. Y, this is probability of.
Yes.
So basically, can I say that this is like f of, can I say it is xi parameterized by mu k and sigma k square. What does that mean? When xi equals to k, then I'll just say that I'll look into that product of y. Correct, no? So let us say okay, k equals to 1 to 3, right?
Yeah.
So when I say that, what is the probability that y equal to small y, that y comes from that small y, given that x equal to k. In other words, what I'm saying that, okay, k is equal to 1. Let us say probability of y given k equals to 1. Then how will I get the probability? From this normal distribution, right? From this distribution, right?
Yeah.
If it is x equal to 2.
Yeah. Mu1 sigma 1 square.
And if I wanted to find x equal to 2, then I will just go for mu 2 and
so based on the value of the x, we will decide the mu and sigma.
And what is that? That is equal to k, right? So, so I can say that k equals to 1, 2, 3 here. So mu k and sigma k square, and so this is the way of writing it, right? There's a density of xi, and that is like
xi,
or maybe you can say y, but based on xi, and whichever xi you will choose, right? I will get the density differently, right?
Yeah, based on the
Because
value of I, K will be given, right?
right, correct, no? It's fine.
Yeah, yeah, okay.
Not xi, okay, let us say x here.
It should be K, SK,
X.
XK.
Okay, let's say xk. It's fine. Yeah, right.
And K will be chosen, no?
That's okay, but yeah, k will be chosen.
Yeah,
That's
okay,
a
okay,
different
okay,
part.
fine.
What is
Yeah, yeah.
this? What is this? Is probability that x equals to k is whatever k will be chosen for me right now. The probability will be if k equal to 1, the probability is 1 by 3. K equals to
Yeah.
probability. So instead of that, I'll say that I do not know. I'll say that it's pi 1, it's pi 2, and it's pi 3. Fine, or pi k. So can I say that it is pi k summation of k equals to 1, 2, 3, right? Right?
Mm-hmm. Pi K into, no? This.
Pi k into
Correct.
because this is the thing, right?
This is the probability. This is the probability, and that is the. Yeah.
Right now, think about this is we have done only for one sample. So how many samples I need to do this if I wanted to find out the likelihood, right? So this is for like I haven't considered like any now number of. So how many samples do I have? How many exercises I'm having? N, right?
N samples.
So can I say that this is like, okay, this is for one data point, right? You agree?
Yeah, yeah, yeah.
One data point. Now how many data points I need to do this? I need to find out
Product of this N,
this
right?
is what the likelihood of
Likelihood.
all these parameters given by, fine.
Theta I.
Okay, I'll say that it's k.
Okay, theta
Theta
x1.
is like everything.
Theta
All
is
this,
all the
all
parameters, 6 parameters. All these 6 parameters and this xi, correct?
not 6. It should
So
be
no, you got it. Yeah.
or like 8.
All these parameters,
This is
yes,
theta. Okay.
in the data.
This is okay. This is fine. Right. So I have already. What is this now? The likelihood function. Right. I hope till this part is fine.
Yes.
What next I need to do? I have to find the log likelihood of this, right? Now because we are using MLE estimator, like you wanted to find out the maximum likelihood estimator for all of this. What is the next step I need to do? I'll find out the log likelihood of this, right?
Log
So
likelihood of
log likelihood of theta given x1 to xn will be what then? This product of something, but basically it will be what, like a product will convert into
sum.
so it will be summation of I equal to 1 to n, right? And then log of sum, not I, here it will be k, 1 to k is pi k into density. Is that fine? Okay. But how does it look like? Let us say it will is it not looking like this? Log of a1 plus log of sorry, I should write like this. Log of a1 plus a2 plus an, and I have sum across 1 to n, or maybe ak, kind of like this
Yeah, it
structure.
is like this.
Or but so now whenever you wanted to find out, so why you use the log here for the likelihood? To flatten out this product, right? Generally what you do whenever we have seen that in maximum likelihood estimator we had the product of likelihood and use log to flatten all these terms so that we can easily differentiate them, right? But now in this case we have got this summation, that's fine, but it is a summation of log of summation, right?
Yeah.
So it is having, so log under, inside the log we again have one more of sum. So you might say that why it is a problem, right? Is that correct?
Yeah, yeah. This is a problem. Yes.
Why it is a problem? Let us say
The
log of
sums.
x square y plus maybe x cube y plus x to the power 4 y. If this is the function, and I think this looks like this, and if I wanted to differentiate this function, let us say this h, so dh by dx, if I wanted to do, how this will be getting it now? It will be 1
One by
upon
this, one by
log of
this,
all into,
all
let us say, 2xy, right? And
one upon log of this or one upon this.
log of all this quantity, right?
Yeah.
Right, no, because if I wanted to do with respect to x, it has to be like this, and then 2xy plus 3x square,
3x
whatever.
square.
So
Right?
this is going to be like pretty much hard, right, to
Yeah,
solve
yeah.
it. Then you will not get, because again this something here, this something here, and we are equating it to 0. Will you get the answer very straightforward? Probably no, right? So
This
this,
part we
yeah,
will not
computation of
find it.
this is pretty hard.
Yeah.
Again, this is not like whatever I shown is like the only the inside part I have shown, right? Again, it is summation is there outside on with respect to the number of data points. So this is computationally hard. So what we use here is Jensen's inequality. Fine. I hope all of you know that Jensen's inequality in terms of whenever we do the convex function and all. So maybe I'll not maybe go through all of this. Maybe I'll directly use that Jensen's inequality because we are out of time. Uh, so okay, what is the Jensen's inequality for the convex? Okay, log is a concave function. All of you know that
The monotonous.
log is a
Yes.
concave function, right? Okay, I think I'll just pretty quickly I'll use this convex function.
Log is convex, no?
No, log is concave.
Concave.
Yeah. So this is convex function, right? I hope all of
Yeah.
you know.
Yes.
If you are done MLF, you'll better know.
Hmm.
So
Convex.
mm, let us say you have these two data points. Okay. I'll just quickly do it. Maybe I hope you should know it, but let us say if you don't know it, like still I'll try to find it out. Like, so A and B are the two data points here. Okay. Uh, I take mean of these two. What will be the mean of these two?
A
A
plus B
plus
by
B
2.
by 2.
A
Fine.
plus B by
These are the x, and let us say this is
Yes.
f of x. So what is f of a? This value is f of a, right?
Yeah.
This value is f of b. Fine.
Yeah.
What will be the actual value for f of a plus b by 2? So the function's actual value will be where? Can you tell me? Where it will cut the graph, right?
Below the
This is f of a plus b by 2. Is that fine?
Yeah.
How you find out the function's value where that will cut, right?
Yeah. Yeah.
I hope all of you know that.
Yes.
Yes, sir.
Yes.
But when we call it as a convex function, is that there is a definition for convex function. A lot of definitions are there. If you have studied MLF, you might have known. If you not, it will come again. But for simplicity, I'll try to say that we will do one thing. We will just uh, use a linear interpolation here. Okay. So you have that line joining these 2 points. So what points exactly we are joining here? A and B, or f of A and f of B?
Yeah.
F
Yeah.
of A and F.
F of A and f of B.
F
Okay.
of B.
Uh, so what this Jensen inequality in terms of the convex function says is that, and if I do that, uh, what is the value? What is this value here?
F of B minus f of A by 2.
What is it? So basically this value is f of a
plus
plus
f
f of b
Plus f of
divided
b
by 2.
by 2.
So this is what I will get, right?
Yeah.
This I'll get here, which I'll get f of a plus f of b by 2. And you can think of this also, right? So this is exactly the centered. So this is like this plus this divided by 2. Okay. So, but actual value of the function is at this point, if a plus b by 2 is what? This one, right? This is
Yeah.
actual value,
Yeah.
right? Actual value of the function
Yes.
at this point. This is 1 point. A plus b by 2 is 1 point. And
Hmm.
the actual value of the function is this. But if I use the interpolation and if I try to see that between a and b, if this point is there exactly at the midway, what will be the value given by this? It is f of a plus f of b by 2, right? Now, for this is for convex functions. So for convex functions, the Jensen's inequality states that uh, the function is qualifies to be a convex function when you join two points, like two random points in that domain, and if you find that the function's value, the actual function's value at that point, a plus b by 2 is
Less than
less
equal
than
to
or equal to f of a plus f
a
of
plus
b
f
by
of
2.
b by 2.
This is for convex
Then,
function.
yeah,
And if you
that is
have a
convex.
and if you have a
Convex.
concave function,
Greater than equal to.
sorry, concave function will be like this, right? So it will be like, so if you join two, so exact is higher than this, right?
Yeah.
So for concave function, it will be like this: f of a plus b by 2 is greater than or equal to f of a plus f of b by 2. So this is true for let us say any. So here we have used like this. We have taken f of a by 2 plus b by 2, right? Half of this
Yes.
plus. So we have used zero point 0.5, 0.5, so zero point 0.5 of a plus 0.5 of b. But can I take any lambda between 0 to 1? And in that case, it will become like this: f of lambda times a plus 1 minus lambda times b, and that will be equals to f of, oh, sorry, that should be, so if you think about this, it is lambda times f of a plus, so it is like proportionately b should be greater than or equal to, for concave function I'm talking about. And this is just for, and here what is here is, so uh, okay, so yeah, that's fine. Okay, and if this is for 2 points, but if you have more than 2 points, in that case it will be some proportions will be there. So lambda 1 a1, let's say, plus lambda 2 a2, and up to, let's say, lambda n an should be greater than or equal to lambda 1 f of a1 plus lambda 2 f of a2 and plus lambda n f of a. Okay, right? And one more thing is, so lambda 1 plus lambda 2 plus lambda n should be equal to 1. So these are the weightage. So what is this actually? Is some, is a weighted sum, right? Weighted sum, right? We are providing some weightages to these points, and what we are saying is the function
So
of
where is this b? This lambda in the second line, lambda a plus 1 minus lambda b, and it was opened lambda 1 a1 plus lambda 2 a2.
not open, this is separate. This is only for 2 points. This for
Okay.
2 points, and this I am saying for n points.
Okay. That is for 2 points. Yeah.
This is expanded.
Yeah.
For
Expansion.
n points, I am saying that lambda 1 plus, if I wanted to use it for 2 points, then how this will look like? It will be lambda 1 plus lambda 2 equals to 1. And what does that mean? Lambda 1 is nothing but 1 minus lambda 2, right?
Yeah, got it.
And then I'll get the above result. Okay, fine. So what we are, so now this is called as the Jensen's inequality, and we are using this here because I'm not, log is what? This is a concave function, right? So what can I say about this quantity? this quantity here is I can say that summation of I equal to 1 to n, right? And we had this log of, what is it, summation of I equal to 1 to k, and what was that, pi k times f of xi parameterized
Xi
by
and
mu k.
mu k and sigma k square.
So what, and but basically what is this? This is a normal distribution, right?
Hmm.
So this is like 1 to n log of, sorry, log of sum of, sorry, sum of I equal to 1 to k pi k into 1 upon, I think, root 2 pi sigma k into e to the power minus
Minus half
xi
xi minus
mu
mu
k
k
whole square by
sigma k
2 sigma square, 2 sigma k square,
sigma
right?
k square here.
Is that fine?
Hmm.
I hope this is fine. Now what I'm trying to say is this quantity is greater than or equal to what? Okay, I think I have to introduce one more parameter here. Maybe I'll introduce one more parameter, which is, which parameter I should include here? This lambda parameter, right? Uh, are you able to see this part? So is that fine? Okay, I think I should write down this. This log is what? This is my log likelihood. Okay, this log likelihood of theta. Now what we'll try to do is we'll try to find out the Jensen's inequality for this part. We introduce new parameters, probably for here. This is my actual problem. What I'm trying to do here is I'll introduce one of the parameters here, maybe lambda k. Is that fine? But if I introduce something here, I should be dividing it by that parameter, right?
Hmm.
Okay. Is the correct quantity here? Yes. Correct, right? Why? Because anyway it is getting cancelled out. Uh, are you able to see this part here?
This is lambda k to the power I.
To the power I is not there. It's like lambda ki.
Yeah.
Must like lambda ki is for the ith data point, right?
I
So
data point.
we have n data points, right? So what I am saying is for
Change the
for
number of the
each,
cluster.
yeah, for each data point, I have to introduce this lambda values. Fine.
Got it.
But then in that also, for each of the cluster, right? Each of the cluster, I need to have different values of lambda. Correct? Here, if you think about this, let us say for any I, for any I, then I have this lambda 1, lambda 2. I is what here? Data point. Or data point, or you can say that one example, right? One data
Yes.
point, the example. And in that we have lambda 1, lambda 2, how many? Lambda k, right? And then this one a1, a2, and an will be what? The values here. So we want it into that fashion. So this thing will write down as ak. Fine. So this will look like summation of I equal to 1 to n log of uh, summation of I equal to 1 to k lambda k power I, not power I, lambda k I into ak. Is that fine? Ak, or maybe aki, I'll write ak is just fine. It's not. Is that okay? See, it's little complicated. You see, it's not like whenever if I say to you, it should be like apparently it will come to you. That is not the case, right? But you have to do yourself. Like you have to watch the lectures again and again. Maybe you'll find it out it better. what I'm saying is this quantity is greater than or equal to what? Huh? So do you feel that this is this kind of like this f of lambda, f of maybe summation of I equal to 1 to k lambda k a k? F is what? Logarithmic function, right? And by using the Jensen's inequality, what we can say about this is greater than or equal to lambda k times f of ak. Is that fine? Or maybe so it should be like summation outside, it will come out, right? I hope this is fine for you guys. No? Okay, maybe I'll write down the Jensen's inequality. We'll get better understanding of it. Okay. This is like, okay, don't worry about this part. Think about this part. What is Jensen inequality says? It's like f of lambda 1 or lambda 1 a1 plus lambda 2 a2 plus lambda k ak is greater than or equal to what? Lambda 1 f of a1 plus lambda 2 f of a2 plus lambda k f of ak. Is that fine? I hope at least this is fine.
Yes. Yes.
Yes, no? Okay. Then in this case, if I wanted to write this compactly, how will I write this compactly? F of summation of I equal to 1 to k lambda k ak
Okay. Yep.
and greater than or equal to summation of I equal to 1 to k lambda k f of ak.
Yes. Lambda can be taken outside.
Yeah.
Is that fine? So think about this function as log, because this can be any function, right? So log of this is equal to what then? Lambda k log of ak,
Yes.
right?
Yes.
But this is only for one data point. So if I wanted it for n number of data points, how it will be like this? So summation of I equal to 1 to n greater than summation of I equal to 1 to n. Is that okay? Any issues now? No? Got it. Summation of 1 equal to n, that is like it's not big deal, right? It's like for each data point we are thinking about that. If you have n number of data points, it will be changing accordingly. Is that fine? Look at it now.
Yes, sir. Probably you'll have to use J or something.
J for what?
Log
I
is
mean-
concave, no? Log is the concave function, no?
Correct.
No. I meant I equal to is being used twice. So
Where it is? Okay,
in
sorry.
sigma, yeah.
Okay, maybe I'll use k or j is fine. Yeah, we'll use k for simplicity. Okay, sorry. Is that fine?
Yes.
K, like maybe small k equal to 1 to k. Is that fine now?
Yes, sir.
So what is this actually for each of the cluster actually we are looking at, right? 1 to k is what? Clusters, right? No, and 1 to n is what? Number of data points. But if you remove this data point part right now, you can actually be able to see this Jensen's inequality, which is written above. Correct, no? Hmm? Right? And what is AK? AK here is pi k,
Function, yeah.
1 upon
Pi
root
k
2
1
pi
upon
sigma k
sigma k root 2 pi
exponential
e to the power x
square by
mu k upon
2 sigma k square
minus 2
by lambda k. Right?
minus 2, no?
What minus 2 where?
Is x exponent e to the power
Okay, sorry. Yeah. Minus. Okay, sorry. Got minus. Is that fine?
Yeah.
Right. This is my AK. Fine. But if this was AK for only one data point, if I have to go for n data points, it will be like here xi will be there and here I will be there. So now this is called as a modified. This is okay with summation of I equal to 1 to n, right? So summation of I equal to 1 to n. This is the modified log likelihood function. I hope that is okay. You may see it later, but this is correct. Huh? Okay. You guys have said said to me that you already have watched lectures, right?
No, it
Probably.
is okay. No,
Okay.
it is okay. We will do it, then it will be more clear because some
Yeah.
complex calculations are there. We will do ourselves, then it will be clear.
Yeah. So what we are saying is now instead of solving for this,
That's why I told, no, exemplification will solve the problem. Some example we will do, no, then it,
log of summation of k equals to 1 to k lambda k ak equal to, sorry, not, it should be greater than equal to what, summation of I equal to 1 to n summation
summation
of
of
I
k
equal to
is equal to 1 to k.
k equal to 1 to k, uh, maybe
You can
lambda.
keep j is equal to 1 to k. It will be better because
Okay,
I
j
think value will be from 1 to k. It will vary, no? The lambda
lambda
k is equal
k,
to lambda
then
k
j,
not j. Now it is j log aj. Yeah,
log of aj. Is that fine?
aj. Yeah,
Okay.
now it is.
Now
Yeah, now it is okay.
we are not solving. We are not going to solve maximization for log likelihood. Instead of, we are going to solve it for this. Now, is this solvable? That is the question, right? Now, is it solvable?
Yeah,
Can solvable in the sense, can we maximize it right now? I think yes. Previously, it was like this sum, right? Uh, Not this one. Probably it was something different. It was pi k into this, pi k into this entire property. Now,
F function.
now it is, we have introduced one more thing, lambda j, and we are going to solve it for this. So it is having two steps. One is, now we have two different parameters, right? All total parameters were how many? Theta. What are those? Pi 1 to pi k, right? Mu 1 to mu k, sigma 1 square to sigma k square, right? Now we have introduced some more parameters, and what are those? Lambda 1 to lambda k, and that is for each of I, right? I will be just 1 to. Is that fine? Right. I hope this is okay. It's I think it's little bit too much for like once you're if you're doing it for the first time, but you will get it. It's not like a very difficult thing to understand if you know what we are doing. Whenever we wanted to apply, I think that is easier for it. So what is the next target to do? So this is okay. This is fine. Now we are saying this. This is called as a modified log likelihood. Log likelihood. This is modified log likelihood, and now what we are saying is we are trying to maximize this part, right? So instead of maximizing the other thing, we are maximizing this modified log likelihood, and what is that? Summation of I equal to 1 to n, summation of, let's say, j equals to 1 to k, and lambda j, and log of aj. Aj is, I'll write down aj for like for the last time right now, then I'll
aj.
not write it down. What is aj? It is pi pi j, right? Pi j into 1 upon root 2, or maybe I can just write it here, pi j root 2 pi sigma j, okay? Okay,
E raised to
e to the power minus xi minus mu j square divided by 2.
Pi j is the notation, no? Pi j means
See,
product
that's
of.
why I didn't wanted you to have that j here. J is like this one, right? The clusters, number of clusters.
Yeah.
So pi for first cluster, pi for second cluster, pi for
Yeah.
up to
Yeah.
k clusters it will be there, no?
Yeah. Okay.
How to
Okay.
sum over all that
Yeah. Yeah.
and divided by
Okay. Yeah. Yeah. Yeah.
lambda j. And this is like its quantity. So the for number of examples, this will change and this will change, right? This part. So xi is not xi is like each of the data point or each of that. I don't know whether you guys be able to understand that, but you know,
Okay. Divided by lambda j.
that lambda j we have used no initially to cancel
Okay.
it out.
That's why you divided it, right?
Because it is there, right? It is already there.
Yeah.
It's
Yeah.
not gone anywhere, right?
Mm.
It has to be somewhere, right? Otherwise, it is not vanished anywhere, na?
Mm.
Correct. Now
Yes.
it will get we'll get rid of that, but okay, that is and we maximize with respect to theta. But theta is what like all these parameters, right? All that pi 1, pi 2, pi k, mu 1, mu 2, mu k, and sigma 1, sigma 2, sigma k, or
Mm.
square of that.
Mm.
Now, what you need to do, you first, okay, first what you do, fix lambda, okay, and now fix the lambda, fine. Lambda, when I say fix lambda means how many lambdas you are going to fix it? Lambda 1 to lambda k, right?
Yeah. K lambdas.
So you fix lambda in the sense you take some values for lambda and now try to find out with respect to let's say mu with respect to sigma. Is that fine?
Mm.
And that mml value comes out to be okay, I'll just write down as it is whatever is there. So mu k hat by using the mle or yeah I think so mle or you can think of that mml is what mml is modified
Well,
modified
maximum likelihood.
likelihood. Okay, so because this mu k is not the maximum likelihood estimate, right? It's not mle, right? This is the modified maximum likelihood because this function is the lower bound, right?
Mm-hmm.
We are maximizing the lower bound of that. We are not maximize the actual likelihood function. This is the actual likelihood function, right? We're not doing that.
Mm.
So and that's why this is called mml, and that comes out to be so these values are there. You may check this in the lecture. This is like summation of I equal to 1 to n lambda what should I say j I then xi divided by summation of I equal to 1 to n j. Okay, then sigma k square mml is equals to summation of I equal to 1 to n lambda ki into xi minus mu hat ml. Okay, so again we have to use this here, right? Square and divided by summation of. So can you see, are you able to see some familiar structure here? It's kind of a sample variance, sample mean and all, but here only thing we have introduced is what the weighted sample mean, right? Its lambdas are there, lambda 1 lambda 2 to lambda n. That's fine for each of the cluster. And now we separately have to maximize for this pi 1 to pi k, which is summation of I equal to 1 to n, and then summation of I j equal to 1 to k probably, and then what is it, lambda k to the power I and log of pi k. Okay, then now you'll ask like why this is, right, from where it is coming. So if you think about this, we wanted to maximize this function, right? Correct? Right? When I wanted to find out the pi values, these values, then in that case, for the fixed lambda, in that case, if I wanted to differentiate it, what should I have to do? I have to treat mu and sigma as constants, right? Right?
Yeah. Yeah.
Yeah, no? So in that case, if you think about this bracket, all of this is constant because sigma I am already fixing, mu is constant, sigma is constant, lambda is constant, right? Lambda we are fixing. So this is constant. So this term is basically what? Log of pi into some constant, right?
Correct.
Correct, right? So anyway, that will not affect me, right? So if it is constant, so it is kind of, I'm just doing it for log of c into pi, fine, and this lambda g is there. So like if it is okay, I'll just give you some example for this. So if I wanted to, let's say, log of 2x and log of x, maybe, or let's say 3 log x and 3 log of 2x, do they have the same differentiation or do they have the different differentiation? So what is the differentiation for this? 1 upon 2x probably, and 3 will be here into 1, or maybe it's 3 by 2x, right? What about
3 by
this?
2x,
Here it is 3 by
3 by x.
x. So what is the change here? It's like nothing, right? It's
First,
some constant.
first, some constant.
So if I just use here, it's like c by 2, or maybe it's another constant, right? Does
Yeah.
it affecting? So if I just write pi k, right, and here it is lambda j, something like that, into pi k, and we have some constant here. Uh, does the derivative affect too much? Because essentially we are going to, if it is, let's say it was 3 by 2x and 3 by x, right? How much it is going to be? Uh, no, right? Like it will not affect much, right? Because it's just a scaling factor, right? And that's why you just when you wanted to find out pi k, in that case, you are treating what, mu and sigma as constants, right? That means basically you are solving this equation, and after solving that, and what constants do we have? It will have some constants, right? What is the constant? Pi k. What is having the pi k constants? What are pi k's? The probability of each cluster occurring, right?
Each cluster.
So pi k j equal to k is equal to 1.
The sum of all the probabilities, yeah.
And what else? Each of the pi k, the probabilities are greater than or equal to 0, right?
Yeah.
So this is the constant optimization problem. Okay, problem, and this is solved by Lagrange's method. Maybe sometime if I get chance, I will tell you what is that if you don't remember it. Fine. Anyway, it will come into MLF, and if you already done MLF, it is there. But okay, so I do not have right now the time to do that. So pi hat MML is coming out to be this. This is like very evident actually. Okay, by n. Is that fine? Now what we did is we fixed lambda and try to find out other parameters. Now one more step I need to do is what? I have to, so all of these are the theta parameters, right? Correct? Now we fix theta and what? Differentiate that maximum likelihood function with respect to what? Lambda. Correct? No, because I need that lambdas also. So if I do that, I'll get Okay, I'll get like very weird expression, but okay, you can actually. It's not that difficult, but yeah, I'm. You can watch the lecture, okay? Because it's already getting 3 hours. It's possible I'll just write it down. Whatever the doubts if you have about this, maybe I can cover it later on. But I think it's like it's nothing but just some simple, mathematics, calculus part divided by 2 sigma k square and divided by summation of I equal to 1 to L 1 to K. Okay, 1 upon root 2 pi sigma j into e to the power minus xi minus mu j square. Okay, I'll have that which is pi. Okay. And yeah, by 2 sigma j square into pi j. Fine. This is the expression we are getting. That is okay. You can see the lecture again for that expression. The thing is, okay, I'll just write down the EM algorithm first. Maybe what you do is again to initialize all thetas. What are those thetas? Pi 1,
Parameters.
yeah, pi 1 to pi k, mu 1 to mu k, and sigma 1 square to sigma k square. Fine. Uh, that is the
So, sir,
initialization.
a quick question.
Hmm.
So we use this algorithm only for normal distributions?
This is for clustering, right? Find out clusters.
Ah, okay.
This is a clustering algorithm, no?
Okay, okay.
What we are saying is these clusters are actually, uh, you know, uh, distributed as per the Gaussian mixture model. Okay, that is our assumption. We are saying that these clusters are uh, distributed according to the Gaussian mixture model. Now, if I assume that it is like that, then what is the probability for selecting or for that data point going into that cluster? So we are finding out the probabilities of each of the data point going into that cluster, right?
Yeah, yeah.
So
Okay.
whenever the probability comes higher, fine.
Yeah.
Uh, so we assign that cluster to it. So basically,
Okay.
I'll tell you that. So we are saying that this is
I
all
got
data
it.
points.
Yeah.
Got it, no?
Yeah. Yeah. Yeah.
So if I pick one point randomly here, now let's say x1. So what we do, you find out the probability for x1, all right, for the cluster one. Okay. Let us say for cluster one, the probability is 0.67. Okay. Or for one indicator, and then it is 0.33, let's say 32. How much it is then? And it's 0.01. So in which cluster it will belong to then? The first
One.
one.
One. Yeah.
So you are actually that's why you need like how will you get these values? If you know
Okay.
these parameters, right? All these parameters, and based on that you would actually calculate the probabilities, and then based on the higher probability you assign that cluster to that point. So previously, what you used to do in k-means clustering, you find out the distances
Correct.
and then you assign the clusters accordingly, right? Here we
Yeah.
are not doing that. What we are finding out the parameters first for that Gaussian mixture model, right? Assuming that all this data point comes from that uh, distribution, and now we are assigning the probabilities, and based on the probabilities we are assigning the cluster.
Okay.
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 So this initialization generally comes from the k-means clustering algorithm, or maybe I can say that uh, you know uh, Lloyd's algorithm, right? And then you perform what? Until convergence, you perform this theta t plus 1. What is it? Theta t plus 1 minus theta. We are giving some threshold, epsilon. What is this theta here? All the parameters. So each of the step, right? So we are, because this is the iterative algorithm, we check theta 0, right? So we have this theta initialized with theta 0, and then we found out theta 1, and now we check the difference between theta 1 and theta 2. If this parameters change drastically more than some epsilon, right, then we stop. right? Sorry, if it is if the difference, right, between the current parameters and the updated parameters, if it is lesser than this, we'll stop. If it is greater than that, then what we'll do, you perform the next step. And what is that step? You first of all, you find out lambda t plus 1, which is arg max of lambda. What is this? And uh, modified log likelihood. You know, right? What is modified log likelihood? Theta t comma lambda. What is that? You have seen that expression, right?
We
So what?
just saw.
Yeah. So what you are doing is, for the fixed theta at that iteration, you found out the different values of lambda. Fine, right? In this step, and in the next step, what you do, you update all the parameters by fixing. Now, what you have to fix? Lambda, right? Modified log likelihood of theta. Now, this will be theta. You are actually working with this expression, and which lambda you will be using here? Lambda t or lambda t plus 1? So in this step, what you did, you kept theta as constant, right? Correct. Okay, I'll show you this expression. This was my problem, right? Is what this entire thing is modified log likelihood, right? Is that okay? What you are doing here is, you fix all these parameters theta constant, or you fix it means like you treat them as constant and you differentiate with respect to lambda, right? Is that okay? Uh, okay. Anybody is understanding here what we are doing?
Yes, sir. Yes, sir.
Right now? Okay. So theta t. So what is theta t? Whatever the parameters we found out in the previous step, we are keeping them as constant, and we differentiate that modified log likelihood function with respect to lambda to get the lambda t plus 1. Okay. And whatever the lambda t plus 1 we have got, in the next iteration, what you do, you differentiate, you take that theta t plus 1, no, sorry, lambda t plus 1, and you differentiate with respect to theta to get that parameters. Okay. In general, and that is what you do. And every time you get this theta t plus 1, you use it here. You try to see that, okay, whether that is under some limit or not. If it is under some limit, then you will stop. Otherwise, you will perform this operation again and again. Fine. This is the algorithm, uh, and this is called as the maximization step. Okay. Maximization step, and this is called as the expectation step. Why it is called expectation step? Uh, if you remember the Jensen's inequality, what was that? Lambda 1 a1 plus lambda 2 a2 plus lambda n an, right? It was a function of that, and we said that it is greater than or equal to, what is it? Lambda 1 f of a1 plus lambda 2 f of a2 plus lambda n f of an, right? And this was our modified function, right? Modified log likelihood function. And can you think that this is kind of, so these lambda ones are the fractions, right? Some fractions, because they sum up to 1, right? So lambda 1 plus lambda 2 plus lambda n, lambda 1 plus lambda 2 up to lambda n, that summation is equal to 1. So that means this lambda 1 is some 0.2, 0.5 or something, 0.3, 0.02 or something like that. And they all add up to 1. Now, if you think about this, so lambda 1 into f of a1. So, if, have you learned about the weighted sum? So, if you heard about it previously, or if it is not also, this or probabilistically, if you think about it, right, this is expected value of the function, right? Have you? Okay, maybe I'll give you some small example to understand. So suppose you have x equal to 1, 2, 3. X takes values 1, 2, 3. Provide that x equals to x is say 0.3, 0.4, and 0.3. Is that fine? What is the expectation of x?
X into p of x equal to x.
So yes, it is kind of summation. So if I think about this, is can I say it is 0.3 into 1 plus 0.4 into 2 plus 0.3 into 3,
3.
right? So if I think of this as lambda 1 into, let's say, f of a1 plus lambda 2 to f of a2 plus lambda 3 f of a3, it looks like some expectation, right?
Correct.
Right. So that's why this step is called as the expectation step, because we are getting the values for lambda, right? Treating every other value is constant. And the next step is what? You are actually now, once my lambdas are fixed, you are actually maximizing the log likelihood, right? This modified log likelihood is a function of what? All these lambdas and the log likelihood function, right? Which we wanted to maximize to get the this is like this theta t plus 1. Actually, these are the parameters which we wanted to estimate, right? I hope you understand that part. And we how do you get that? By maximizing the likelihood function, right? And this is the step, and that's why it is called the maximization step, and this is called as the expectation step. And from that, this e from expectation step and m from the maximization step, and that is called as the em algorithm. Okay, you go through these lectures again so that you'll better clarify it, because if you're listening to this for the first time, I doubt that you'll grasp like all of the things, but I tried my best to tell you the things. Okay, this em algorithm, whatever the clusters it will produce, right, they are called as soft clusters. Why? And why the k-means is the hard clustering? Because in k-means cluster you are actually you are actually finding out the Euclidean distances, and based on those distances you are assigning the clusters, right? And that means whenever the cluster is assigned to any data point, it will not be probabilistic, right? It is deterministic. It is definitely, it belongs to that cluster, right? But in em algorithm, what you do, you provide the probabilities to that data point, where the data point belongs to. Let us say that x1 data point belongs to cluster 1, it is having some probability. With x2 it is having some probability, and it is x3 is having some probability, and whichever is the highest probability, we assign the data point to that cluster. That is why it is called as a soft clustering, because if x1 belongs to the cluster 1 is having, let's say, probability of 5.51, right? Belongs to let's say, or maybe I can say that point 505, and here it is 0.9, and let's say this is for cluster 1, is for cluster 2, and this is for cluster 3, is 0.05. Then this cluster will belong to which one? Cluster 1, right?
Yes.
But even though it is having good chance to go to cluster 2, right?
Correct.
But we are not like, we are not going to so this is kind of, it's not very hard clustering, right? It is based on the probabilistic approach, and hence it is called as the soft clustering. Okay, uh, and that is why hard clustering, because it is like whatever the data point it will go, right, it is definitive, because we have counted the distance of the data point from each of the centroid in k-means clustering, and based on that we have come up to the decision. There is no kind of probability involved in that. That is why they provide the hard clusters. Also, since now, will that give me the Warner regions, the CM algorithm? No, correct? It's
Could
like
you repeat the
it
question,
can,
sir?
whatever the clusters produced, right? Do they belong to the Warner regions? Like Warner regions, right? Whatever the centroids you have, you kind of take a perpendicular to that. So ordinary regions are all the perpendicular intersections of those in the k-means clustering. Remember or no?
I missed the third week. That's why.
Okay, fine. Then you can probably go back and see. Yeah, few points I have missed today to explain, but if you go through the lectures, you'll get it. I tried to cover like most of the part, and only four of you are here, so maybe we'll stop here today. Fine.
Yeah, you completed the lecture, right, sir? We
Yeah.
under.
Everything is completed. Like almost like maybe few additional details are there. You can just check out later.
Yeah.
Okay. Okay. Fine.